Welcome to Quiet Universe, the place where we leave behind the chaos of Earth and drift into the vastness of space. Tonight, we're cracking open one of the most fascinating chapters in space exploration history, the 1970s. It was a decade of wild dreams and even wilder achievements, where humanity's gaze turned from our home planet to the mysteries of the cosmos. Imagine a world where engineers and scientists, armed with calculators, slide rules, and unshakable optimism, dared to send machines to places we'd only glimpsed through telescopes. The Moon, Mercury, Mars, Jupiter, and the edge of our solar system. Nothing was off limits. This wasn't just exploration. It was a cosmic declaration that we were here, ready to learn, and not afraid to fail. Over the next few moments, we'll unravel the awe-inspiring stories of missions like Luna 16, robotic courier from the Moon, Pioneer 10, the brave pathfinder through the asteroid belt, Mariner 10, the first to unlock Mercury's secrets, Viking 1 and 2, the Martian trailblazers, and Voyager 1 and 2, the twin emissaries now sailing through interstellar space. So grab a cozy blanket, let your imagination wander, and let's dive into an era when space wasn't just the final frontier. It was the frontier we were boldly conquering. Ready to journey back to the 1970s? Let's go. Luna 16 stands out in the annals of space exploration as a testament to human ingenuity and the relentless pursuit of understanding the cosmos. Launched by the Soviet Union in September 1970, this mission marked the first successful robotic retrieval of lunar soil. What made Luna 16 truly remarkable was the fact that it accomplished this feat without any human presence on the Moon, relying solely on complex engineering and innovative robotics. This was at a time when the idea of machines independently performing intricate tasks millions of kilometers away was groundbreaking. The mission demonstrated how humanity could extend its reach into the unknown, not just with astronauts, but through autonomous systems that could operate in environments hostile to human life. The technical execution of Luna 16's sample return was nothing short of extraordinary. After landing in the Sea of Fertility, the spacecraft deployed a drill to penetrate the lunar surface and collect a cylindrical core of soil about 35 centimeters deep. This process was meticulously pre-programmed, requiring an exquisite understanding of lunar conditions and the ability to anticipate every possible challenge. The collected sample was then sealed in a canister, placed inside the ascent stage, and launched back to Earth. What made this process so groundbreaking was its precision. Every step needed to be executed flawlessly, without real-time human adjustments. At a time when communication delays with robotic spacecraft were significant, this was a bold leap in demonstrating the capabilities of autonomous systems. The lunar samples returned by Luna 16 offered fascinating insights into the Moon's geology. Weighing just 101 grams, the material included fragments of basalt and tiny grains of minerals that helped scientists better understand the Moon's volcanic past. Unlike the Apollo missions, where astronauts could collect diverse samples by hand and visually assess their surroundings, Luna 16 relied solely on its drill, meaning its collection was more focused on subsurface material. This offered a unique perspective, evidence of the Moon's deeper layers that hadn't been as thoroughly explored by previous missions. For researchers, even such a small sample provided a treasure trove of information, enriching our understanding of lunar formation and the processes that shaped its surface. When compared to the Apollo missions, Luna 16's approach highlighted the contrast in how robotic and human exploration tackle similar objectives. Apollo astronauts could roam across the lunar surface, selecting samples based on real-time observations and intuition, bringing back extensive collections. Luna 16, however, relied on pre-designed programming to drill into a single, predetermined spot. While Apollo brought back hundreds of kilograms of diverse samples, Luna 16's modest haul was nonetheless significant because it proved that robotic missions could achieve complex tasks autonomously. This was especially important for the Soviet Union, which had not achieved manned lunar landings, but demonstrated through Luna 16 that they could still advance space exploration in remarkable ways. The success of Luna 16 resonated deeply within the global scientific and engineering communities. It wasn't just about the soil it returned, but the demonstration of what was possible with robotics and careful planning. For a world that was beginning to grasp the vast potential of space, Luna 16 represented a pivotal moment. It showed that human exploration didn't always require humans to be physically present. It was a mission that laid the groundwork for future endeavors, proving that robotic systems could complement and even substitute human presence in space. In many ways, Luna 16 expanded the horizons of what we dared to imagine, ushering in a new era of space exploration where machines became our trusted partners in venturing into the unknown. Luna 16 was a marvel of Soviet engineering, embodying a blend of innovation and practicality in its design. It consisted of several key components, each meticulously crafted to ensure the mission's success. The spacecraft was composed of an ascent stage and a descent stage. The descent stage was responsible for the delicate task of landing on the moon, equipped with engines, landing legs, and sensors to ensure stability on the uneven lunar surface. The ascent stage housed the container for the lunar soil, as well as the propulsion system needed to return the sample to Earth. Every element of Luna 16 was a testament to the ingenuity of its designers, who had to account for the harsh conditions of space and the moon's lower gravity while ensuring that the entire system could operate autonomously. The heart of the mission, the sample collection mechanism, was an engineering triumph in itself. It was essentially a drill attached to a robotic arm, designed to extract a core of lunar soil from beneath the surface. The drill had to be both robust and precise, capable of penetrating the moon's tough regolith while ensuring the sample remained intact during extraction. Once the soil was collected, it was transferred to a hermetically sealed container to preserve its integrity during the return journey. This mechanism operated flawlessly, a feat made even more impressive considering it was pre-programmed to function without human intervention. The entire process, from drilling to sealing the sample, was a delicate ballet of mechanical precision executed millions of kilometers away. The propulsion system that powered Luna 16 to and from the moon was another critical aspect of the mission. The spacecraft relied on a combination of liquid-fueled engines for both its lunar descent and its ascent back into space. The descent stage used its engines to perform a controlled landing, reducing speed and ensuring a safe touchdown on the lunar surface. After the sample was collected, the ascent stage's engine ignited to propel the container into lunar orbit. From there, it rendezvoused with the return trajectory back to Earth. This sequence required not only impeccable engineering but also precise calculations to ensure every burn of the engine was executed at the right time and with the right force. The propulsion system was the lifeline of the mission, dictating its success or failure at every stage. The amount of lunar soil collected by Luna 16 was modest by comparison to manned missions, just 101 grams. But the method of retrieval made it an invaluable achievement. The core sample was taken from a depth of approximately 35 centimeters, offering a glimpse into the moon's subsurface layers. Unlike the Apollo missions, which allowed astronauts to make on-the-spot decisions about which rocks or soil to collect, Luna 16's sample was determined by the programming of its robotic systems. Despite the small quantity, this soil provided critical data about the moon's geological history and proved that automated systems could gather scientifically significant material. The telemetry and communication systems of Luna 16 were the invisible threads that tied the spacecraft to Earth, allowing engineers to monitor its progress and adjust its operations when needed. These systems relied on radio waves to transmit data back to mission control. Information about the spacecraft's health, position, and activities was sent in real time, while commands from Earth guided the craft through its most complex maneuvers. The distance between the Earth and Moon posed a challenge, with communication delays of several seconds, but the reliability of Luna 16 systems ensured smooth coordination throughout the mission. This was a time when computer systems were still in their infancy, yet the spacecraft's ability to relay data and respond to instructions highlighted the incredible foresight and technical skill of its creators. Every aspect of Luna 16's design and operation reflected the resourcefulness of the engineers and scientists behind it. They worked within the constraints of their era: limited computational power, the unknowns of space exploration, and the geopolitical pressures of the Cold War, to create a spacecraft capable of achieving a feat that had never been done before. Luna 16 was more than just a machine. It was a symbol of human determination to push boundaries and expand our understanding of the universe, even in the face of immense challenges. Luna 16 emerged in a tense geopolitical climate at the height of the Cold War, when space exploration was as much about scientific discovery as it was about demonstrating technological superiority. By 1970, the United States had already achieved its monumental Apollo 11 landing, putting humans on the moon and securing a major victory in the space race. For the Soviet Union, Luna 16 was not just a scientific mission but a statement to the world. It showcased that they, too, could achieve groundbreaking lunar exploration, albeit through a different approach. While the Americans focused on human spaceflight, the Soviets turned to robotics, proving they could innovate in ways that rivaled the complexity and ambition of manned missions. The mission was part of the USSR's broader lunar exploration program, which aimed to achieve various milestones in space through robotic probes. Luna 16 was a continuation of efforts to explore the moon's surface, following missions like Luna 9, the first to achieve a soft landing, and Luna 15, which attempted a sample return but failed. It was clear by this point that the Soviet strategy had shifted. With the Apollo program capturing the world's attention through dramatic human endeavors, the USSR sought to carve out its legacy in robotic exploration. Luna 16 was an essential piece in this strategy, focusing on automated sample retrieval, a feat that required precision engineering and innovation to accomplish successfully. The challenges faced by the USSR in realizing Luna 16 were immense. The space program operated under intense political pressure, with every success or failure scrutinized as a reflection of the nation's technological prowess. Early Luna missions had experienced numerous setbacks, from launch failures to unsuccessful landings. Engineers were tasked with developing systems that could function reliably in the vacuum of space, endure extreme temperature fluctuations, and operate independently in an environment where real-time human control was impossible. On top of these technical hurdles, they had to contend with limited computing technology and the ever-present demand to outperform their American counterparts. Luna 16 was as much a triumph of perseverance as it was of technology, overcoming these obstacles to achieve its historic mission. Compared to earlier Luna missions, Luna 16 represented a significant leap forward in both technology and ambition. The early Luna probes were primarily experimental, designed to gather basic data about the moon's surface and test landing techniques. By contrast, Luna 16 was a highly sophisticated spacecraft with a clear scientific objective: to collect and return a sample of lunar soil. It incorporated advanced guidance systems, precision landing technology, and a groundbreaking sample collection mechanism. These advancements reflected the lessons learned from previous missions, as well as the evolving capabilities of the Soviet space program. Luna 16 was not just about reaching the moon but demonstrating a new level of technological mastery. In the context of the space race, Luna 16 played a unique and strategic role. By 1970, the race to put a human on the moon was over, but the competition between the superpowers had shifted to other domains of space exploration. The Soviet success with Luna 16 showed the world that they remained a formidable force in space. It was a counterbalance to Apollo, proving that robotic missions could achieve complex tasks and deliver valuable scientific results. For the Soviet Union, this mission was a source of national pride, a reminder that their space program could still push the boundaries of what was possible. It also laid the groundwork for future robotic exploration, influencing the development of later missions and shaping the trajectory of lunar science. Luna 16 was more than just a spacecraft. It was a symbol of the era's fierce competition and the resilience of the engineers and scientists who worked under extraordinary pressures. Each success was hard-won, the product of countless hours of labor and an unwavering belief in the possibilities of human ingenuity. At its core, Luna 16 embodied the spirit of exploration, reminding the world that progress often comes in many forms, even amidst the turbulence of geopolitical rivalries. Luna 16 was launched aboard a Proton-K rocket, the workhorse of the Soviet space program, chosen for its proven capability to carry heavy payloads beyond Earth's orbit. The Proton-K had already been used in several earlier lunar missions, and its reliability and power made it the natural choice for sending a sophisticated spacecraft like Luna 16 to the moon. The rocket's design reflected decades of engineering refinement, with its multiple stages providing the thrust needed to escape Earth's gravity and precisely position the spacecraft on a trajectory toward the moon. Its selection wasn't just a matter of capability, it was also a matter of confidence. The engineers understood that the margin for error was razor-thin. Even a small failure during launch could spell the end of years of work. The journey to the moon was meticulously planned, and each milestone brought its own challenges. After separating from the Proton-K's upper stage, Luna 16 entered a parking orbit around Earth before a carefully timed engine burn sent it hurtling toward the moon. The spacecraft had to travel over 380,000 kilometers, adjusting its course along the way to ensure it reached the right destination. As it approached the moon, another critical engine burn slowed it down, allowing it to enter lunar orbit. This phase of the mission required pinpoint accuracy, as any miscalculation could have sent the spacecraft careening off into space or crashing into the moon's surface. The entire process was a delicate dance of physics and engineering, with the mission team relying on their understanding of celestial mechanics and the spacecraft's onboard systems to guide Luna 16 to its target. The choice of Luna 16's landing site in the Sea of Fertility was no accident. This region was selected based on data from earlier missions, which indicated that it offered relatively smooth terrain, making it ideal for a safe landing. The site also held scientific interest, as its basaltic plains were thought to provide valuable insights into the moon's volcanic history. Determining the landing site wasn't just about minimizing risk. It was also about maximizing the scientific return. The mission planners had to balance these factors, knowing that a successful sample return depended on the spacecraft's ability to land on a surface that was neither too rocky nor too steep. Even with the best planning, however, the final moments of the descent were fraught with uncertainty. The descent and landing posed some of the most significant challenges of the mission. As Luna 16 approached the moon, its descent engine fired to slow the spacecraft down, while onboard instruments worked to ensure a controlled landing. The spacecraft relied on radar to measure its altitude and velocity, adjusting its thrust in real time to guide it to the surface. However, the moon's uneven terrain and low gravity added layers of complexity. The landing had to be soft enough to avoid damaging the spacecraft, but precise enough to keep it upright and stable. Every second of the descent was critical, with no room for error. When Luna 16 finally touched down, it was a moment of triumph, a testament to the careful design and programming that had gone into the mission. The return of the lunar samples to Earth was a feat of engineering that underscored the mission's complexity. After collecting the soil sample, Luna 16's ascent stage ignited, lifting the sample container off the lunar surface and into orbit around the moon. Timing was everything. The ascent stage had to achieve the correct trajectory to ensure it could escape lunar orbit and head back toward Earth. Once on its return path, the sample container separated from the spacecraft, re-entering Earth's atmosphere at high speed. A heat shield protected the container from the intense heat of re-entry, and a parachute deployed to slow its descent, ensuring a safe landing on Soviet soil. The recovery team had to act quickly to retrieve the container, knowing the world was watching and waiting to see the results of their groundbreaking mission. Every step of this process was a delicate balance of precision and innovation, executed under the intense pressure of making history. The success of Luna 16 was met with widespread acclaim from the global scientific community, as it represented a monumental step forward in robotic space exploration. Even in the midst of Cold War rivalries, scientists from around the world recognized the significance of the mission. The ability to retrieve lunar soil without human intervention demonstrated the extraordinary potential of robotics in exploring remote and inhospitable environments. Researchers were eager to study the 101 grams of lunar material returned by Luna 16, knowing that every new sample added valuable insights to humanity's understanding of the moon's history. While nationalistic pride certainly surrounded the mission, the scientific achievements it represented transcended political boundaries, sparking admiration and respect even among those on the other side of the geopolitical divide. For the Soviet Union, Luna 16 was a much-needed boost to its standing in the space race. By 1970, the USSR had faced setbacks, particularly in the wake of the United States' success with the Apollo 11 and 12 missions, which had brought humans to the moon. The robotic return of lunar soil allowed the Soviets to reassert themselves as pioneers in space exploration. It was a clear demonstration that their expertise in autonomous spacecraft was second to none, and it reinforced their narrative that space exploration could take many forms, not just those involving human astronauts. This achievement also provided a morale boost domestically, serving as a reminder of Soviet technological prowess and their ability to compete with the United States in the high-stakes arena of space. In the United States, Luna 16's achievements were acknowledged with a mix of respect and pragmatism. NASA scientists, while focused on their own ambitious lunar programs, understood the technical sophistication involved in a robotic sample return mission. Privately, there was admiration for the ingenuity required to achieve such precision with automated systems. Publicly, however, the mission received less attention as the Apollo program continued to dominate headlines and the imagination of the American public. The success of Luna 16 didn't diminish the achievements of the Apollo program, but it served as a reminder that the Soviet Union remained a formidable competitor. It was a subtle shift in the narrative of the space race, one that emphasized the complementary roles of human and robotic exploration. Criticisms and controversies surrounding Luna 16 were relatively few but not absent. Some Western observers argued that the mission, while impressive, lacked the inspirational quality of human exploration, suggesting that it was a response to the USSR's inability to send cosmonauts to the moon. Others pointed to the limited quantity of lunar soil returned, comparing it unfavorably to the hundreds of kilograms brought back by Apollo missions. Within the Soviet Union itself, there were internal debates about the direction of the space program, with some questioning whether the focus on robotics was a concession in the face of American dominance in human spaceflight. These critiques, however, did little to overshadow the mission's technological triumph or its significance in advancing lunar science. The legacy of Luna 16 extended far beyond its immediate impact, influencing the future of lunar and planetary exploration. It proved that robotic missions could achieve complex objectives autonomously, setting the stage for more advanced probes in the years to come. The techniques and technologies developed for Luna 16 paved the way for subsequent Soviet missions, such as Luna 20 and Luna 24, which refined the sample return process. Globally, Luna 16 inspired a broader appreciation for the role of robotics in space exploration, influencing the design of future missions to Mars, asteroids, and beyond. Its success highlighted the versatility and cost-effectiveness of robotic systems, a lesson that continues to shape the priorities of space agencies to this day. Luna 16 wasn't just a milestone in the space race. It was a foundation for the future of exploration, reminding humanity that the pursuit of knowledge is a shared endeavor, one that transcends borders and political rivalries. The technological innovations introduced by Luna 16 left an enduring legacy in the field of space exploration, influencing everything from robotic mission design to planetary sample return strategies. One of its most significant contributions was the development of a fully automated sample collection and return system. The precision drilling mechanism and the sealed container for safely transporting lunar soil demonstrated that robotic probes could perform highly complex tasks without direct human involvement. This innovation laid the groundwork for future missions, such as NASA's Mars rover Perseverance, which aims to collect Martian samples for eventual return to Earth. The ability to conduct such missions autonomously remains a cornerstone of modern planetary exploration, particularly as humanity looks toward distant worlds where human presence is currently impossible. Scientifically, Luna 16 added a unique layer to our understanding of the Moon. The soil sample it returned, while modest in quantity, was significant in its origin. Taken from the Sea of Fertility, the material provided insights into the composition and geological history of lunar basalt plains. The sample revealed details about the Moon's volcanic activity and helped refine estimates of its age. By comparing the Luna 16 sample with those collected by Apollo missions, scientists were able to build a more comprehensive picture of the Moon's evolution. Luna 16's contribution was a reminder that every piece of lunar material, no matter how small, holds a story about the processes that shaped our nearest celestial neighbor. This mission proved that even robotic probes could make discoveries that resonate across the scientific community. The lessons learned from Luna 16 remain remarkably relevant today. Chief among them is the importance of redundancy and precision in designing autonomous systems for space exploration. The mission showed that even with limited computational power, careful planning and robust engineering could enable a spacecraft to perform complex, time-sensitive operations millions of kilometers away. This principle continues to guide robotic missions, from the European Space Agency's Rosetta probe to NASA's OSIRIS-Rx, which recently collected samples from an asteroid. Luna 16 also demonstrated the value of meticulous site selection and pre-mission planning, a lesson that is applied today when deciding landing zones for rovers or habitats on extraterrestrial bodies. Its success serves as a reminder that breakthroughs often come from balancing ambition with careful execution. There are few physical artifacts or monuments explicitly commemorating Luna 16, but its achievements are preserved in the broader narrative of space exploration history. The lunar soil it returned remains a scientific treasure, stored and studied by researchers eager to unravel its secrets. In Russia, Luna 16 is remembered as a triumph of Soviet engineering and ingenuity, often featured in exhibitions and retrospectives on the space program. While it may lack the iconic status of Apollo 11's first lunar landing, it holds a respected place among the milestones that shaped humanity's exploration of space. Its legacy is a quiet but profound one, often referenced as a benchmark for robotic sample return missions. In popular culture and historical narratives, Luna 16 occupies a unique space as a symbol of human perseverance in the face of technological and political challenges. While it hasn't inspired blockbuster films or widespread public fascination, it represents a quieter heroism, the kind that comes from overcoming daunting odds with ingenuity and determination. For those who study the history of space exploration, Luna 16 is a poignant reminder that progress doesn't always come with fanfare. Sometimes, it's a small container of lunar soil that tells a story of immense scientific and technical achievement, one that continues to echo in the missions we launch today and in our unending quest to explore the cosmos. The total cost of the Luna 16 mission remains an elusive figure, as the Soviet Union, unlike NASA, did not publicly disclose detailed budgets for its space missions. Estimates suggest that Luna 16 and other robotic lunar missions were significantly more cost-effective than the Apollo program, which spent billions on manned exploration. This efficiency was partly a result of the Soviet Union's reliance on automation and its focus on achieving strategic objectives with minimal resources. Even without an official figure, it is clear that the mission was an economical triumph, achieving its objectives without the immense logistical challenges and costs associated with human spaceflight. For the USSR, Luna 16 wasn't just a scientific success, but also a demonstration of how resourcefulness could deliver world-class results in space exploration. The lunar samples returned by Luna 16 offered some intriguing findings that added nuance to our understanding of the Moon. The soil, collected from the Mare Fecunditatis, Sea of Fertility, contained basaltic material that helped confirm the volcanic origins of the lunar Maria. One unexpected discovery was the precise mineral composition of the sample, which differed slightly from the samples brought back by the Apollo missions. This variation highlighted the diversity of lunar geology and underscored the importance of collecting materials from multiple locations on the Moon. The data also contributed to refining theories about the Moon's formation and its thermal history. While the sample was small, just 101 grams, it was a powerful reminder that even a handful of lunar soil can unlock vast amounts of information about our celestial neighbor. The timeline of Luna 16's mission was impressively short, reflecting the precision and efficiency of its design. From its launch on September 12, 1970, to the return of its sample capsule on September 24, the mission lasted just 12 days. In that brief period, the spacecraft traveled to the Moon, successfully landed, collected its sample, and returned to Earth. A tightly choreographed series of events that left little room for error. This swift turnaround demonstrated the effectiveness of the mission's engineering and planning, setting a standard for future robotic missions that aim to achieve high-value objectives in a limited time frame. Despite its success, Luna 16 wasn't entirely free of technical challenges. Like any pioneering mission, it faced moments of uncertainty, particularly during its descent and landing. The lunar surface posed a complex environment, and ensuring a stable touchdown required the spacecraft systems to perform flawlessly under conditions that could not be fully replicated on Earth. Additionally, the ascent stage, tasked with launching the sample container into lunar orbit, relied on precise timing and flawless operation to ensure the soil reached Earth. While there were no major anomalies reported, the mission team operated under constant pressure, knowing that even a minor glitch could jeopardize the entire mission. Their success in navigating these challenges speaks volumes about the robustness of their designs and their ability to anticipate and mitigate potential risks. The media coverage of Luna 16 was shaped by the geopolitical climate of the time. In the Soviet Union, the mission was heralded as a triumph of socialist engineering and scientific prowess. State-controlled media highlighted the mission's achievements, framing them as proof of the USSR's continued leadership in space exploration. Globally, the reaction was more subdued, overshadowed in part by the United States Apollo program, which had already captivated public attention with its manned lunar landings. Nonetheless, scientific communities around the world recognized the significance of Luna 16, and it was reported as an important milestone in space exploration. The mission may not have commanded front-page headlines in every corner of the globe, but for those following the progress of the space race, it was a clear signal that the Soviet Union remained a formidable player in the quest to understand and explore the Moon. Luna 16 and the Apollo missions occupied different realms of space exploration, each contributing in ways that reflected their respective priorities and technological philosophies. While the Apollo missions dazzled the world with human footprints on the lunar surface and returned hundreds of kilograms of diverse samples, Luna 16 represented the ingenuity of achieving similar goals through automation. The scientific contributions of Luna 16, though modest in volume compared to Apollo's troves, were still groundbreaking. Its samples, retrieved from the Sea of Fertility, provided data that complemented the Apollo findings and reinforced a broader understanding of lunar geology. Luna 16 also demonstrated the value of robotic missions, particularly in scenarios where the logistics and cost of human involvement would be prohibitive. While Apollo symbolized human exploration, Luna 16 underscored the power of robotics to reach extraordinary milestones independently. The success of Luna 16 set the stage for subsequent missions in the Luna program, each building on its achievements. Luna 20, launched in 1972, returned another sample from a different location, the Apollonius Highlands, adding to the diversity of lunar materials available for study. Luna 24, in 1976, marked the final chapter in the Soviet Union's lunar exploration efforts, successfully retrieving samples from a depth of nearly 2 meters below the surface. An impressive technical feat that extended the scientific value of robotic sample return missions. These missions refined the technologies pioneered by Luna 16, from sample collection mechanisms to autonomous return systems, and collectively established a legacy of efficiency and precision in lunar exploration. When compared to modern robotic lunar missions, such as China's Chang'e series, Luna 16 stands as a pioneering ancestor. China's Chang'e 5, for instance, shares Luna 16's goal of returning lunar samples, but it operates with the benefit of advanced technology, far superior sensors, computing power, and precision. Chang'e 5 also collected samples from a region of the Moon never explored before, reflecting the continued evolution of site selection and mission objectives. However, the fundamental principles of Luna 16's mission remain evident in these modern endeavors. It is a testament to how foundational ideas developed decades ago continue to shape and inspire even the most advanced space exploration programs today. Luna 16's influence extends beyond lunar exploration, inspiring robotic sample return missions targeting a variety of celestial bodies. Japan's Hayabusa missions to asteroids, NASA's OSIRIS-RX, and even future plans for Mars sample return missions owe a debt to the groundwork laid by Luna 16. These missions have adopted and expanded upon the principles of autonomous operation, efficient sample collection, and safe return to Earth. Luna 16 proved that it was possible to conduct high-stakes, unmanned sample return missions successfully, providing a template for future endeavors to retrieve material from increasingly distant and challenging environments. Reflecting on Luna 16 offers a glimpse into the evolution of space exploration technology. The mission emerged from an era of limited computational power and relatively rudimentary sensors, yet it accomplished a task that would still be considered sophisticated today. Its success highlights the importance of ingenuity, problem-solving, and incremental progress in the development of space technology. Over the decades, the lessons of Luna 16 have been refined and incorporated into the DNA of modern missions, showing how early breakthroughs serve as stepping stones for the next generation. Luna 16 reminds us that each mission, whether from the past or the present, contributes to an ongoing story of human curiosity and the relentless pursuit of understanding our place in the universe. Pioneer 10 was a bold step into the unknown, a spacecraft designed to accomplish feats that no machine had attempted before. It became the first spacecraft to cross the asteroid belt, a region once thought to be a graveyard for interplanetary missions. Engineers in the early 1970s feared the dense cluster of rocks and debris between Mars and Jupiter could destroy any spacecraft that ventured through it. Yet Pioneer 10 defied those fears. Equipped with a sturdy structure, it carried a protective Whipple shield, a layer designed to absorb impacts from small particles. As it navigated this celestial obstacle course, Pioneer 10 demonstrated that the asteroid belt was far less dense than once imagined, paving the way for future explorations. This triumph was not merely a technological feat. It was a testament to human curiosity and courage in venturing into the uncharted. Reaching Jupiter was another monumental milestone for Pioneer 10. Before this mission, humanity's understanding of Jupiter came only from telescopic observations, which offered limited clarity about the planet's swirling storms and enigmatic moons. Pioneer 10 became our first emissary to this giant world, sending back close-up images that were both mesmerizing and groundbreaking. As it approached, its instruments captured the intricate details of Jupiter's Great Red Spot, its dynamic cloud bands, and its immense magnetosphere. The spacecraft didn't just photograph. It measured radiation levels, detected the solar wind's interaction with Jupiter's magnetic field, and mapped the planet's intense magnetosphere. Each image and data packet brought the planet closer, no longer just a distant speck of light in the night sky, but a tangible world of awe and wonder. Pioneer 10's journey wasn't just about achieving planned objectives. It was also about uncovering the unexpected. For instance, as it traversed the asteroid belt, it discovered that the region wasn't as perilous as once believed. It also measured cosmic rays and interstellar particles, revealing new insights about the environment beyond Earth's protective bubble. While passing Jupiter, it identified the planet's strong radiation belts and their profound effects on its surroundings. These findings weren't merely academic. They were clues to understanding how planetary systems form and evolve. Pioneer 10's sensors, designed for exploration, often became instruments of discovery, showing that even well-prepared missions could be surprised by the cosmos. Surviving Jupiter's intense radiation was a testament to Pioneer 10's robust design. Jupiter's magnetosphere is the largest structure in the solar system, filled with charged particles that could fry electronics in moments. Yet the spacecraft endured this hazardous environment thanks to its thoughtful engineering. Its instruments were encased in aluminum to shield them from radiation, while its electronic systems were designed with simplicity and redundancy. This wasn't just cold engineering. It was the result of humans anticipating every possible threat, adapting designs, and trusting their ingenuity to protect the mission. The fact that Pioneer 10 emerged unscathed from Jupiter's radiation belts showed the resilience of human creativity when faced with seemingly insurmountable challenges. Perhaps the most poignant part of Pioneer 10's story lies in what it carried: a message from humanity to the stars. The spacecraft bore a gold-anodized aluminum plaque, etched with symbols intended to communicate with any intelligent life that might one day encounter it. Designed by Carl Sagan and his colleagues, the plaque included a depiction of a man and woman, a map of Earth's location in the galaxy, and a diagram of hydrogen, the most abundant element in the universe. This wasn't just a scientific gesture. It was a profoundly human act. It spoke of hope, of connection, of a desire to reach beyond our small world and tell the universe that we exist. Even as Pioneer 10 ventured into the silent void, it carried with it the voices and dreams of the people who sent it. Pioneer 10's mission wasn't just an exploration of space. It was an exploration of what humanity could achieve when we dared to dream beyond the horizon. Its legacy lives on, a testament to our relentless pursuit of knowledge and our unyielding curiosity about the cosmos. Pioneer 10 was a marvel of engineering, a spacecraft meticulously designed to achieve what had never been done before. At its heart were the instruments that enabled it to unravel the mysteries of space. It carried a suite of devices, each with a specific purpose. The imaging photopolarimeter was tasked with capturing the first-ever close-up views of Jupiter, transforming a distant gas giant into a realm of intricate cloud patterns and swirling storms. The magnetometer measured magnetic fields, revealing the powerful magnetosphere of Jupiter and providing clues about the structure of the asteroid belt. Radiation detectors gauged the intensity of cosmic rays and the hazardous radiation belts surrounding Jupiter, vital data for future missions. Other instruments, such as the Geiger Tube Telescope and Charged Particle Experiment, worked together to study high-energy particles in space. These instruments were not just tools but extensions of human curiosity, allowing us to observe and understand a distant frontier. Crossing the asteroid belt was one of Pioneer 10's most daunting challenges, and its design reflected the risks it faced. Engineers had to consider the possibility of collisions with micrometeoroids and debris, which could puncture or damage the spacecraft. To mitigate this, they equipped it with a Whipple shield, a protective barrier designed to absorb impacts from small, fast-moving particles. The spacecraft itself was compact and streamlined, minimizing its vulnerability to debris. Redundant systems were built into its design to ensure that even if one part failed, the mission could continue. Every detail, from the layout of its instruments to the materials chosen for its construction, spoke of the care and forethought of the people who built it. They understood the stakes and ensured that Pioneer 10 could withstand the unpredictable hazards of its journey. Powering a spacecraft bound for the outer reaches of the solar system required an energy source as reliable as it was efficient. Pioneer 10 used a radioisotope thermoelectric generator, RTG, which converted heat from decaying plutonium-238 into electricity. This choice of power was both practical and innovative, as solar panels would have been ineffective so far from the sun. The RTG provided a steady stream of energy, enabling the spacecraft to operate its instruments and maintain communication with Earth for decades. By the time Pioneer 10 sent its last faint signal in 2003, it had outlived its expected lifespan many times over, a testament to the durability of its design and the foresight of its creators. Communication with Pioneer 10 was another triumph of ingenuity. Sending data across billions of miles required a powerful and precise system. The spacecraft used a high-gain antenna, a dish designed to focus its signals into a narrow beam directed toward Earth. It transmitted using radio waves, which could travel vast distances through space. On the receiving end, giant antennas from NASA's Deep Space Network captured these faint signals, decoding the invaluable data they carried. The delays in communication, minutes to hours, depending on the spacecraft's distance, were a reminder of the vastness of space and the patience required to explore it. Despite these challenges, the system worked flawlessly for decades, bridging the gap between a small machine in the void and the people who waited to hear its story. Navigating through the solar system required precision, and Pioneer 10's trajectory and propulsion system were designed with care. It relied on a combination of gravity assists and carefully planned course corrections to achieve its objectives. After launch, its trajectory was adjusted using small thrusters to ensure it reached the asteroid belt safely and on target. When it approached Jupiter, the planet's immense gravity was used to slingshot the spacecraft onto a new path, propelling it toward the outer reaches of the solar system at incredible speeds. This technique not only conserved fuel but also demonstrated the elegant interplay of physics and engineering. Each maneuver was calculated by teams of scientists and engineers, whose calculations ensured that Pioneer 10 could navigate the vast, empty distances with precision. It was more than just a spacecraft following a path. It was the culmination of human determination and the relentless pursuit of exploration. Pioneer 10 emerged at a pivotal moment in the 20th century, a time when the space race between the United States and the Soviet Union was evolving. By the early 1970s, the intense rivalry that had characterized the race to the moon had shifted focus to broader exploration of the solar system. The mission symbolized not just technical achievement, but also the optimism of an era when humanity began to view space as a shared frontier. While earlier milestones like the moon landing were about demonstrating superiority, Pioneer 10 was about pushing boundaries, exploring uncharted regions, and asserting humanity's ability to go beyond. It marked the first tangible step into the vast realm beyond Mars, positioning the United States as a leader in interplanetary exploration and setting a new standard for ambitious space missions. NASA's goals in the 1970s were ambitious yet clear: to expand knowledge of the solar system and develop the technologies required for deep space exploration. Pioneer 10 fit seamlessly into this vision. The mission was designed to gather unprecedented data about the outer planets and the environment of space itself. By targeting Jupiter, the largest and most enigmatic planet in the solar system, NASA sought to answer fundamental questions about planetary atmospheres, magnetic fields, and radiation environments. Pioneer 10 wasn't just about exploration for its own sake. It laid the groundwork for future missions like Voyager, Galileo, and Cassini. It was a bridge between the era of planetary flybys and the more advanced orbital missions that would come later, helping to refine techniques and strategies for exploring distant worlds. The Cold War cast a long shadow over every major scientific endeavor during this period, and Pioneer 10 was no exception. Although the mission was primarily scientific, its success had significant geopolitical implications. Demonstrating the capability to send a spacecraft beyond Mars and safely navigate it through the asteroid belt showcased the United States' technological prowess. The data collected by Pioneer 10 wasn't just shared among scientists. It served as evidence of the nation's ability to innovate and lead in a highly competitive global arena. Beyond its symbolic value, the mission advanced humanity's understanding of the universe during a time when such achievements were often framed as a contest of ideologies. Yet, even in the midst of this rivalry, Pioneer 10 represented a unifying human endeavor. Its plaque and message were designed not for nations, but for the cosmos. The mission also built on the legacy of earlier Pioneer programs, which had laid the groundwork for NASA's foray into deep space exploration. The Pioneer series initially focused on studying the moon, the sun, and interplanetary space. These earlier missions provided valuable lessons in spacecraft design, navigation, and data transmission, directly influencing Pioneer 10's development. Engineers drew on the successes and failures of these prior missions to create a spacecraft capable of withstanding the unique challenges of the outer solar system. Pioneer 10 was a culmination of this lineage, embodying the lessons learned and extending the program's legacy into unprecedented territory. Planning and funding Pioneer 10 presented significant challenges for NASA, especially in an era of shifting priorities and tightening budgets. The Apollo program had consumed substantial resources, and as it wound down, NASA faced increasing pressure to justify its expenditures. Convincing policymakers to support a mission to an unvisited part of the solar system required not only scientific arguments, but also the ability to frame the mission as a cost-effective way to advance human knowledge. Engineers and scientists had to innovate within the constraints of limited resources, designing a spacecraft that was compact, efficient, and durable. Despite these hurdles, the mission's team persevered, driven by a shared belief in the importance of exploration. The result was a spacecraft that not only met but exceeded expectations, proving that even in the face of fiscal and political constraints, great achievements were still possible. Pioneer 10 began its historic journey aboard an Atlas Centaur rocket, a choice that reflected both its proven reliability and its capability to deliver a payload into deep space. The Atlas Centaur was a workhorse of the early space age, combining the raw power of the Atlas booster with the precision of the Centaur upper stage. This combination provided the thrust needed to escape Earth's gravity and the finesse to place Pioneer 10 on its precise interplanetary trajectory. The launch on March 2, 1972, was a flawless execution, a testament to the meticulous planning and coordination of NASA engineers and scientists. As the rocket roared skyward, it carried with it the hopes and dreams of an entire generation eager to explore beyond the familiar confines of the inner solar system. As Pioneer 10 approached the asteroid belt, the mission reached a critical phase. At the time, the belt was shrouded in mystery and apprehension. Many believed it was a dense field of debris that could easily destroy a spacecraft. But instead of blindly plunging into the unknown, NASA used every resource available to chart a safe course. Observations from Earth-based telescopes and earlier missions helped identify regions of lower debris density, guiding Pioneer 10 through the safest path. Once inside the belt, Pioneer 10's onboard instruments began measuring particle densities and studying the environment, confirming that the belt was far less hazardous than once feared. This realization didn't just secure the spacecraft's safety. It opened the door for countless missions to follow. Navigating Pioneer 10 to Jupiter was a delicate ballet of physics and precision. Without the ability to course-correct in real time, engineers relied on detailed calculations and mid-course adjustments using the spacecraft's small thrusters. These adjustments, guided by data from tracking stations on Earth, ensured that Pioneer 10's trajectory would intersect with Jupiter at exactly the right moment. Gravity played a key role as well. As the spacecraft approached Jupiter, the planet's immense gravitational field pulled it in, accelerating it and altering its path in what's known as a gravity assist. This maneuver not only allowed Pioneer 10 to gather data about Jupiter, but also propelled it onward toward the outer solar system, extending the mission far beyond its original objectives. The flyby of Jupiter was a highlight of Pioneer 10's journey, yielding scientific observations that transformed our understanding of the giant planet. As the spacecraft approached, it captured stunning images of Jupiter's turbulent atmosphere, revealing intricate cloud bands and the Great Red Spot in unprecedented detail. Beyond the visual spectacle, Pioneer 10's instruments measured the planet's powerful magnetic field, discovering that it was far larger and more dynamic than previously imagined. The spacecraft also mapped Jupiter's radiation belts, whose intensity was a surprise even to seasoned scientists. These observations weren't just academic. They laid the foundation for all subsequent missions to Jupiter, from Voyager to Juno, by providing crucial data about the planet's environment. To ensure Pioneer 10's trajectory avoided collisions with asteroids, NASA adopted a strategy that balanced preparation with adaptability. Before launch, scientists meticulously analyzed the asteroid belt structure, identifying regions where debris density was likely to be lower. This analysis guided the selection of the spacecraft's initial path. But once Pioneer 10 was underway, its instruments continuously monitored its surroundings, detecting any unexpected hazards. The spacecraft's small thrusters gave it the ability to make minor adjustments if necessary, though such maneuvers were rarely required. The real triumph, however, was the success of the planning itself. By combining theoretical models with practical observations, NASA proved that the asteroid belt could be navigated safely, a critical step in humanity's quest to explore the outer planets and beyond. Pioneer 10's journey captured the imagination of scientists and the public alike, creating a sense of awe that transcended the scientific community. For scientists, it was a watershed moment. The data streaming back from billions of miles away validated decades of theoretical work and expanded our understanding of the solar system in ways no one had thought possible. The spacecraft's success in navigating the asteroid belt, a region once thought perilous to the point of impassability, was itself a monumental achievement, demonstrating that deep space exploration was not only feasible but ripe with opportunity. The public, too, was entranced. Pioneer 10 became a household name, its story a rare intersection of complex science and universal human wonder. News outlets and classrooms buzzed with tales of its daring voyage, and for many, it symbolized humanity's capacity to dream and achieve the extraordinary. When Pioneer 10 sent back its first close-up images of Jupiter, the reaction was electrifying. Until then, Jupiter had been little more than a fuzzy disk through a telescope, a giant mystery lurking in the night sky. Pioneer 10 transformed that abstraction into a tangible world. Its images revealed swirling clouds, intricate banding, and the great red spot with detail that was both beautiful and deeply instructive. These images changed the way scientists viewed the gas giant, inspiring countless questions about its atmosphere, composition, and internal structure. The mission also measured Jupiter's massive magnetic field and radiation environment, information that would prove essential for designing future missions. Pioneer 10 didn't just illuminate Jupiter. It redefined what was possible in planetary science, proving that remote, high-resolution exploration could yield discoveries that fundamentally reshape our understanding of the cosmos. The influence of Pioneer 10 on subsequent interplanetary missions was profound. Every spacecraft that ventured into the outer solar system owes a debt to Pioneer 10's pioneering achievements. Its successful navigation through the asteroid belt and its radiation-hardened design set new benchmarks for spacecraft durability. Its use of a gravity assist at Jupiter became a template for efficient interplanetary travel, a technique employed by later missions like Voyager and Galileo. Even the design of its instruments, with their ability to collect and transmit data over vast distances, served as a blueprint for future exploratory technology. The lessons learned from Pioneer 10's triumphs and its occasional challenges helped refine the planning, engineering, and execution of deep space missions, ensuring they were as resilient and resourceful as their predecessor. Pioneer 10 also carried with it a cultural and philosophical resonance that extended beyond its scientific achievements. The spacecraft bore a golden plaque, a message intended for any extraterrestrial beings who might encounter it. Designed by Carl Sagan and his colleagues, the plaque featured a diagram of the spacecraft, a map of our location in the galaxy, and human figures. This gesture of cosmic outreach was both humble and ambitious, symbolizing humanity's desire to connect, to be known, and to acknowledge its place in a vast, mysterious universe. Pioneer 10 became more than a spacecraft. It became a cultural icon, representing humanity's curiosity and our shared longing to explore the unknown. Its achievements prompted philosophical debates about our role in the cosmos, inspiring art, literature, and countless dreams of what lies beyond. Internationally, Pioneer 10 was viewed with admiration and respect, even by countries competing with the United States in the space race. Space agencies around the world recognized the technical ingenuity and scientific importance of the mission. It set a precedent for collaboration, as data from Pioneer 10 was shared with scientists globally, fostering a sense of collective achievement. In an era often defined by political divisions, the success of Pioneer 10 served as a reminder of what could be achieved through cooperation and shared purpose. It underscored the universal nature of exploration, a pursuit that transcends borders and speaks to the common curiosity that unites humanity. Pioneer 10 stands as a defining milestone in the history of space exploration, marking humanity's first steps into the vastness beyond the asteroid belt. Its significance lies not only in the unprecedented technical achievements of its time, but also in the courage it embodied, a willingness to venture into the unknown with no guarantees of success. It was the first spacecraft to give us a close-up look at Jupiter, an accomplishment that bridged the gap between imagination and reality. Beyond that, Pioneer 10 was the first human-made object to chart a course out of the solar system, forever redefining the boundaries of exploration. Its journey symbolizes humanity's transition from studying nearby worlds to daring to dream of interstellar travel, making it a cornerstone of our collective journey into space. The mission deepened our understanding of two enigmatic regions, the asteroid belt and Jupiter. Pioneer 10 revealed that the asteroid belt, once feared as an impassable minefield of rocks, was far more navigable than expected. By directly measuring particle densities and the distribution of debris, the spacecraft dispelled myths and cleared the way for countless future missions. At Jupiter, Pioneer 10 provided groundbreaking insights into the planet's composition, its colossal magnetic field, and its intense radiation belts. These discoveries painted a picture of a dynamic, complex world that profoundly shaped subsequent planetary science. The data not only helped refine our theories about Jupiter, but also enhanced our understanding of giant planets in general, offering clues about the formation and evolution of the solar system. The design and engineering of Pioneer 10 have left an indelible mark on modern spacecraft. Its radiation-hardened systems, built to withstand Jupiter's punishing environment, set a precedent for durability in extreme conditions. The spacecraft's reliance on a gravity assist at Jupiter demonstrated the feasibility of using planetary slingshots to extend mission lifespans and reduce energy requirements, a strategy now standard in interplanetary travel. Its simple yet robust instrumentation showed that even relatively small spacecraft could yield extraordinary scientific returns. The lessons learned in building and operating Pioneer 10, particularly in managing long-distance communication and data transmission, have influenced the development of more advanced probes like Voyager, Cassini, and New Horizons, all of which owe some part of their success to the pioneering work done decades earlier. Today, Pioneer 10 drifts silently in the interstellar void, its mission long complete but its legacy enduring. The spacecraft's last week signal was received in 2003 after traveling more than 12 billion kilometers from Earth. It is now coasting away from the Sun, heading toward the constellation Taurus, where it will continue its journey for millennia. While it no longer transmits, its presence is a testament to human ingenuity, a tangible reminder of our early efforts to explore beyond our planetary neighborhood. Pioneer 10 is now a ghostly traveler, carrying its golden plaque into the cosmos, a message in a bottle cast into the infinite sea of stars. The legacy of Pioneer 10 is alive and well in modern interstellar missions. Projects like Voyager, which followed in its wake, and contemporary endeavors like the James Webb Space Telescope and the Conceptual Interstellar Probe are all built on the foundation it established. The mission also continues to inspire dreams of sending spacecraft to other star systems, with initiatives like Breakthrough Starshot aiming to carry Pioneer 10's spirit of exploration to the next level. By showing what was possible with limited technology and boundless ambition, Pioneer 10 remains a guiding light for those who seek to push the boundaries of what humanity can achieve, reminding us that the stars are not just distant points of light. They are destinations waiting to be explored. Pioneer 10's mission was filled with discoveries that surprised even the most seasoned scientists. One of the most striking findings came from its encounter with Jupiter. The spacecraft detected radiation levels far higher than anyone had predicted, revealing the immense and hostile environment surrounding the gas giant. These measurements forced scientists to rethink how radiation interacts with planetary magnetic fields and how spacecraft could be protected in such conditions. Another unexpected discovery was the vast extent of Jupiter's magnetosphere, which stretched millions of miles and confirmed the planet's status as a true giant among its neighbors. These insights didn't just fill gaps in our understanding. They reshaped our entire perspective on the outer planets and their role in the solar system. Pioneer 10 demonstrated remarkable longevity, continuing to send data back to Earth for more than 30 years. Its final, faint signal was received on January 23, 2003, when the spacecraft was over 12 billion kilometers from Earth. For decades, it provided valuable information not just about its primary targets, but also about the outer reaches of the solar system, where the influence of the Sun begins to wane. Even as its power levels dropped and its instruments fell silent one by one, the spacecraft carried on, embodying the resilience and determination of the mission's creators. That last transmission wasn't just a technical milestone. It was a poignant moment, a farewell from a distant traveler that had served far beyond its original mandate. The Pioneer plaque is one of the most iconic elements of the mission, a message from humanity to the cosmos. Designed by Carl Sagan, Frank Drake, and artist Linda Salzman Sagan, the plaque is a simple yet profound artifact. It depicts a man and a woman standing side by side, the spacecraft itself as a reference for scale, and a map of pulsar locations to indicate Earth's position in the galaxy. The decision to include this plaque was both bold and optimistic, a way to say, "We are here, and we seek connection." It represents not just a moment in scientific history, but a philosophical statement about humanity's place in the universe. The idea of sending such a message sparked debates about the risks and merits of announcing our presence to unknown civilizations, but it also highlighted our intrinsic desire to reach out and be part of something larger. During its journey, Pioneer 10 encountered its share of challenges and anomalies, some of which tested the ingenuity of its engineers. Early in the mission, as it approached the asteroid belt, there was considerable anxiety about potential collisions or damage from debris. Although the spacecraft passed through without incident, the lack of real-time control meant every maneuver carried an element of risk. Later, as Pioneer 10 neared Jupiter, the intense radiation environment caused some temporary disruptions in its systems, forcing mission control to adapt and respond quickly. These moments underscored the delicate balance between careful planning and the need for improvisation in uncharted territory, lessons that would prove invaluable for future missions. The success of Pioneer 10 captured the public's imagination in a way few scientific endeavors had before. Its achievements became a symbol of humanity's ability to push beyond the familiar and into the unknown. The vivid images of Jupiter, the audacity of the golden plaque, and the sheer scale of the mission's ambition reignited interest in space exploration, particularly during a time when enthusiasm for such projects was beginning to wane. Pioneer 10 reminded people of the boundless possibilities that lay beyond Earth, inspiring generations of scientists, engineers, and dreamers to look up at the night sky and see not just stars, but destinations waiting to be explored. Pioneer 10 directly influenced the design and objectives of its successor, Pioneer 11. While both spacecraft shared similar core designs, compact, lightweight, and equipped with nuclear power sources, Pioneer 11 benefited from lessons learned during its predecessor's mission. Engineers fine-tuned the shielding to better protect instruments from radiation, a necessity after witnessing the intensity of Jupiter's environment. Pioneer 11 also expanded on its siblings' achievements by targeting Saturn, becoming the first spacecraft to visit the ringed planet. This dual-planet approach allowed scientists to build a more comprehensive picture of the outer solar system, extending Pioneer 10's groundbreaking legacy with additional discoveries and refinements in interplanetary navigation. Comparing Pioneer 10 to the Voyager missions highlights a leap in technological ambition and capability. While Pioneer 10 was designed primarily for reconnaissance, providing foundational data about the asteroid belt and Jupiter, the Voyagers were equipped for a grander mission, exploring the outer planets and continuing on to interstellar space. Voyager's instruments were more advanced, with higher resolution cameras and a broader range of scientific tools. They also carried the famous Golden Records, a more elaborate cultural artifact than Pioneer's plaque. However, Pioneer 10 paved the way for the Voyagers by proving that such long-duration missions were possible. It demonstrated that spacecraft could survive the harsh environments of deep space and that communication over billions of kilometers could be maintained effectively. When placed alongside contemporary missions like Mariner and Viking, Pioneer 10's achievements stand out for their audacity and scale. The Mariner missions, focused on Venus and Mars, operated closer to home, while the Viking program centered on Mars exploration, including landers. Pioneer 10, by contrast, ventured into uncharted territory, not only traveling farther than any spacecraft before, but also tackling unique challenges like the asteroid belt and Jupiter's intense radiation. The success of all these missions collectively showcased NASA's growing expertise in space exploration, but Pioneer 10's journey to the outer solar system marked a new frontier, laying the groundwork for interplanetary and interstellar exploration on an unprecedented scale. NASA's interplanetary programs were profoundly shaped by Pioneer 10's accomplishments. It demonstrated the effectiveness of using nuclear power sources for deep space missions, a practice that became standard for exploring regions where solar power was insufficient. The mission's data about Jupiter and the asteroid belt informed the planning and engineering of subsequent missions, ensuring their instruments and designs were equipped to handle similar challenges. Additionally, Pioneer 10's use of a gravity assist trajectory at Jupiter influenced the trajectory planning of future missions, including Voyager, Galileo, and New Horizons. By pushing technological and conceptual boundaries, Pioneer 10 expanded NASA's vision for what space exploration could achieve, inspiring ever more ambitious missions to follow. Modern equivalents of Pioneer 10 include spacecraft like New Horizons and the upcoming interstellar probe concept. New Horizons, which conducted a flyby of Pluto in the Kuiper Belt, carries the same spirit of boundary-pushing exploration, venturing into the outer reaches of the solar system to gather unprecedented data. Missions like Parker Solar Probe, while focused on the Sun, reflect Pioneer 10's ethos of tackling extreme environments. Meanwhile, ongoing studies for interstellar missions aim to build on Pioneer 10's legacy, envisioning spacecraft capable of not just leaving the solar system but actively exploring the interstellar medium. These modern endeavors owe a profound debt to Pioneer 10, whose journey remains a cornerstone of humanity's quest to understand the cosmos. In the 1970s, space exploration was pushing the limits of what was thought possible. Among the groundbreaking missions of that era, Mariner 10 stood out. It became the first spacecraft to visit Mercury, an achievement born out of ingenuity and a touch of audacity. What made this milestone even more remarkable was that it had never been done before. Mercury is an incredibly challenging planet to reach, given its proximity to the Sun. The Sun's immense gravity requires spacecraft to burn a significant amount of energy just to slow down and approach Mercury's orbit. Mariner 10 overcame these challenges by pioneering innovative techniques, such as gravity assists, to make the mission possible with the technology of the time. One of the defining moments of the Mariner 10 mission was its use of Venus for a gravity assist. The concept, while theorized, had never been attempted before. Engineers at NASA realized that by carefully timing Mariner 10's trajectory, they could use Venus's gravitational pull to alter its speed and direction, effectively slingshotting the spacecraft toward Mercury. It was an elegant solution to a complex problem, born from a combination of mathematical precision and a deep understanding of celestial mechanics. This maneuver not only conserved fuel but also opened up a new era of interplanetary exploration, showing that the seemingly insurmountable distances between planets could be bridged with careful planning and ingenuity. Mariner 10's journey to Mercury wasn't just a technical feat. It also transformed our understanding of the planet. At the time, Mercury was a largely mysterious world, glimpsed only through telescopes. When Mariner 10 arrived, it revealed a surface scarred by craters, resembling our moon far more than expected. This similarity hinted at a tumultuous early history for Mercury, shaped by massive impacts during the formation of the solar system. But the spacecraft's most surprising discovery was Mercury's magnetic field. Scientists had assumed the small, rocky planet would have cooled and become geologically inactive long ago, with no active magnetic field. Instead, Mariner 10 detected a field that, though weak, suggested that Mercury's core was at least partially molten. This finding forced a re-evaluation of planetary formation theories and left a tantalizing mystery about what was keeping the core active. Taking detailed images of Mercury was no small feat. The planet orbits so close to the Sun that the glare and heat pose serious challenges for observation. Mariner 10 had to strike a delicate balance, navigating close enough to capture high-resolution images without overheating or being overwhelmed by solar radiation. Engineers equipped the spacecraft with a sunshade and carefully planned its orbits to minimize exposure to extreme conditions. The images it returned were astonishing, showcasing a rugged, cratered landscape with stark contrasts of light and shadow. These photographs became the foundation for much of our current understanding of Mercury's surface and its geological history. The mission of Mariner 10 also marked the end of NASA's Mariner program, a bittersweet conclusion to a series of missions that had revolutionized planetary science. By the time Mariner 10 had completed its final flyby, it had exhausted its fuel supply and could no longer adjust its trajectory or communicate with Earth. It was left drifting through space, a silent testament to the ingenuity of the people who built and operated it. The decision to conclude the Mariner program came down to practical considerations. NASA was shifting focus to new challenges, such as the Viking missions to Mars and the Voyager probes destined for the outer planets. Yet, Mariner 10's legacy endured, not just in the data it collected but also in the inspiration it provided to a generation of scientists and engineers. It proved that even the smallest planets could hold the greatest mysteries, waiting to be unraveled by human curiosity and determination. Mariner 10 was a masterpiece of 1970s engineering, a spacecraft that pushed the boundaries of what was possible in space exploration. At the heart of its mission were its instruments, carefully designed to unlock the secrets of Mercury and Venus. It carried a television camera system equipped with 2 cameras to take detailed images of planetary surfaces. The ultraviolet spectrometer was there to analyze atmospheric compositions, while the infrared radiometer measured thermal emissions to study surface temperatures. An array of magnetometers and charged particle detectors were on board to investigate Mercury's magnetic field and the solar wind's behavior. Each instrument was not just a piece of hardware but a product of years of meticulous design, built with the understanding that this spacecraft had one shot to deliver groundbreaking science. One of Mariner 10's most innovative features was its use of solar radiation pressure for attitude control. Spacecraft orientation is typically managed by thrusters, but Mariner 10 supplemented this with a clever technique. Using the pressure exerted by sunlight itself, by tilting its solar panels, the spacecraft could steer itself, much like a sailboat using the wind. This approach conserved precious fuel, a critical factor in such a long and demanding mission. It was a delicate balancing act, requiring precise calculations and constant monitoring by mission controllers, who had to adjust for variables like the intensity of sunlight and the spacecraft's changing position. The propulsion system was another marvel of ingenuity. Mariner 10 used a monopropellant hydrazine engine, a choice that balanced reliability with the demands of the mission's complex trajectory. The engine provided the thrust needed for course corrections and fine-tuning the spacecraft's path, particularly during the gravity assist at Venus and the subsequent flybys of Mercury. Every burn had to be executed with pinpoint accuracy. Even a slight miscalculation could have sent Mariner 10 off course, potentially dooming the mission. The precision of these maneuvers spoke to the expertise of the engineers and the growing sophistication of space navigation techniques. Mariner 10 was powered by 2 solar panels, each stretching out from its body like wings to capture sunlight and convert it into electricity. These panels provided the energy to run its instruments and communication systems, but the mission faced significant challenges with energy management. The spacecraft's proximity to the sun posed a dual problem: ensuring the solar panels didn't overheat while also preventing the rest of the spacecraft from being overwhelmed by the sun's intense radiation. Engineers devised a sunshade to shield critical components and carefully monitored the power demands of the instruments, ensuring that no system drew too much energy at any given time. The technological innovations of Mariner 10 left an indelible mark on space exploration. Beyond its scientific achievements, the mission pioneered techniques that became staples of future missions. Its use of gravity assists demonstrated the potential for navigating the solar system more efficiently, a method later employed by missions like Voyager, Galileo, and Cassini. Its approach to attitude control using solar radiation was a precursor to solar sail technology. The modular design of its instruments, allowing for high-quality data collection within stringent weight and power constraints, set a new standard for spacecraft engineering. Mariner 10 wasn't just a mission. It was a proof of concept for many of the strategies that would define the next era of planetary exploration. It showed that with careful planning and innovative thinking, even the most daunting challenges could be met. In the backdrop of the Cold War, Mariner 10's mission symbolized more than just scientific exploration. It was a demonstration of technological and intellectual prowess. By the 1970s, the frantic pace of the early space race had slowed, but the competition between the United States and the Soviet Union remained fierce. While the Soviets were focusing heavily on Venus and Mars, NASA turned its attention to Mercury, a planet largely overlooked and unexplored. Successfully reaching and studying Mercury allowed the U.S. to expand its lead in planetary science, showcasing innovation not just in reaching far-flung destinations, but in unraveling the mysteries of our solar system's most enigmatic planet. The mission was a quiet but clear statement. Even amid shifting priorities, NASA could still push the boundaries of what was achievable. Mariner 10 was also part of NASA's broader exploration objectives in the 1970s, an era of deep space exploration. While human spaceflight had captured global attention during the Apollo program, NASA was now channeling significant effort into robotic missions. These missions aimed to map, photograph, and analyze other planets, laying the groundwork for a better understanding of the solar system. Mariner 10 fit perfectly within this framework. It was not just about Mercury, but about proving concepts like gravity assists and refining techniques for interplanetary navigation. The mission's success also paved the way for future probes, showing that even the most logistically challenging planets could be reached and studied. The scientific motivation to explore Mercury stemmed from its unique position in the solar system. As the smallest and closest planet to the Sun, Mercury was thought to hold clues about planetary formation and evolution under extreme conditions. Scientists wanted to understand why it had such a high density, what its surface was like, and whether it had any atmosphere or magnetic field. These questions weren't just about Mercury. They were about understanding planetary systems as a whole, including Earth. Mercury's harsh environment and proximity to the Sun made it a natural laboratory for studying extreme solar and geological processes, making it a compelling target for exploration. Mariner 10 stood on the shoulders of its predecessors in the Mariner program. Earlier missions had already demonstrated the feasibility of reaching other planets, with Mariner 2 becoming the first successful interplanetary mission by visiting Venus and Mariner 4 capturing the first images of Mars. Each mission built upon the last, improving technologies and refining methods for navigating space and collecting data. Mariner 10 took these lessons and applied them to an even more ambitious goal, using the gravity assist maneuver pioneered by engineers to chart a path to Mercury. It was a culmination of everything learned in the Mariner series, and its success became the program's crowning achievement. Despite its scientific and strategic importance, Mariner 10 faced significant challenges in funding and planning. By the early 1970s, NASA's budget was shrinking, and public interest in space exploration had waned after the Apollo moon landings. Every mission had to compete for limited resources, and Mariner 10 was no exception. To secure funding, the team had to emphasize the mission's scientific value and potential to make history. The planning phase was equally challenging. With limited computing power and the need to execute complex maneuvers like the Venus gravity assist, the mission required extraordinary precision and coordination. Yet, even amid these constraints, the team persevered, driven by a shared belief in the mission's significance and the desire to push humanity's understanding of the cosmos further. Mariner 10 began its historic journey aboard an Atlas Centaur rocket, a reliable workhorse for NASA during the 1970s. This particular rocket was chosen for its proven capability to launch interplanetary missions with precision and the power required to send Mariner 10 on its complex trajectory. The Atlas Centaur provided the initial boost, propelling the spacecraft away from Earth's gravity and into a solar orbit. With a combination of brute force and finesse, it delivered Mariner 10 onto a path that would take it toward Venus, the first critical milestone on the way to Mercury. Designing Mariner 10's trajectory was an intricate dance with celestial mechanics. The mission's planners had to calculate a path that would not only reach Mercury, a challenge in itself due to the Sun's gravity, but also include a flyby of Venus. By using Venus for a gravity assist, Mariner 10 gained the additional velocity needed to reach Mercury without carrying an impossible amount of fuel. The trajectory was so precise that even tiny deviations could have derailed the mission. Engineers relied on constant tracking and minor course corrections to ensure that the spacecraft arrived at each target exactly as planned. This dual flyby design not only saved resources, but also demonstrated the potential for gravity assists in future missions. The journey to Mercury was not without its challenges. Early in the mission, Mariner 10 encountered issues with its star tracker, a device used for navigation by locking onto a reference star. Glitches caused the spacecraft to lose its orientation, requiring quick-thinking engineers to devise workarounds from millions of miles away. Solar radiation pressure, a force exerted by sunlight, also caused unexpected shifts in the spacecraft's position. While this phenomenon was used for attitude control, it sometimes behaved unpredictably, forcing constant adjustments. Each challenge tested the resilience and ingenuity of the team on the ground, making the mission's successes all the more satisfying. The milestones of Mariner 10's mission were a testament to the careful planning and execution behind the project. After its launch on November 3, 1973, the spacecraft performed its gravity assist flyby of Venus on February 5, 1974. This event not only redirected Mariner 10 toward Mercury, but also provided an opportunity to study Venus's atmosphere with its ultraviolet spectrometer. The first flyby of Mercury occurred on March 29, 1974, marking humanity's closest approach to the innermost planet. Two more flybys followed on September 21, 1974, and March 16, 1975, with each one capturing additional data and imagery. These encounters revealed Mercury's cratered surface, magnetic field, and tenuous exosphere, forever changing our understanding of the planet. Capturing detailed images of Mercury posed a unique challenge due to its extreme brightness and proximity to the Sun. The spacecraft's imaging system needed to balance sensitivity with durability. Engineers developed a special sunshade to protect the camera sensors and other components from overheating. Additionally, they carefully calibrated the cameras to handle high-contrast conditions, ensuring that the details of Mercury's surface wouldn't be washed out by the intense sunlight. Each image had to be timed and positioned precisely, as the spacecraft only had limited windows during its flybys to capture the planet's surface. These images, painstakingly planned and executed, became the foundation for much of what we know about Mercury today, making every moment of Mariner 10's mission a triumph of human ingenuity and perseverance. Mariner 10's findings about Mercury captured the imagination of scientists and the public alike, providing a rare glimpse into a world so close to the Sun yet so mysterious. For the scientific community, it was a watershed moment. Decades of theoretical speculation were finally met with hard evidence. Images, data, and measurements that reshaped planetary science. Mercury, which had been an enigma, now had a face. A cratered surface reminiscent of the Moon, a magnetic field that hinted at a molten core, and temperatures that pushed the limits of what was thought possible for a planetary body. For the public, these discoveries were equally enthralling. The idea that Mercury, scorched by the Sun's heat, could still harbor a dynamic magnetic field was a revelation. Newspapers and television broadcasts brought the distant planet into living rooms, sparking curiosity and a renewed appreciation for the complexity of our solar system. The mission's groundbreaking discoveries were as profound as they were unexpected. Mariner 10 revealed Mercury's surface to be heavily cratered, challenging previous assumptions that it might resemble Earth's volcanic or tectonic landscapes. This finding suggested that Mercury's geologic activity had ceased billions of years ago, leaving a surface largely untouched since the solar system's early history. Even more surprising was the detection of a magnetic field. This was completely unexpected for a small planet like Mercury, which should have cooled and become geologically inert long ago. The discovery suggested that Mercury's core was at least partially molten, forcing scientists to rethink their understanding of planetary interiors. These insights made Mercury a key puzzle piece in understanding planetary formation and evolution. The success of Mariner 10 had a ripple effect on the planning of future planetary missions. Its use of a gravity assist maneuver became a template for subsequent missions, proving that such techniques could extend the reach of spacecraft while conserving fuel. This paved the way for ambitious missions like Voyager, which used gravity assists to explore the outer planets. Mariner 10 also highlighted the importance of flybys as a method for gathering data, a strategy later employed by missions such as Galileo and New Horizons. Its success demonstrated that even the most logistically challenging targets, like Mercury, were within reach with careful planning and innovative engineering. This confidence emboldened NASA and other space agencies to aim higher and farther. However, not everyone was entirely satisfied with the mission. Some criticisms emerged, particularly concerning the limited coverage of Mercury's surface. Because of Mariner 10's trajectory and the alignment of the planet during its flybys, the spacecraft was only able to image about 45% of Mercury's surface. While the data gathered was invaluable, many scientists were left hungry for more. Additionally, there were questions about the cost-effectiveness of the mission, especially as NASA's budget tightened in the wake of the Apollo program. These criticisms, while valid, didn't overshadow the mission's overall achievements but did highlight the growing pressures faced by space exploration programs. Internationally, Mariner 10's mission ignited broader interest in exploring the inner planets. Its discoveries underscored the value of studying planets like Mercury and Venus, not just for their intrinsic interest but for the insights they offered into planetary processes and Earth's own history. The mission showed that exploring our solar system wasn't just an American endeavor. It was a global quest for knowledge. Other space agencies, inspired by Mariner 10's success, began planning their missions to the inner planets, leading to a wave of international collaboration and competition in planetary science. In many ways, Mariner 10 bridged the gap between the early days of the space race and the era of cooperative exploration, leaving an enduring legacy that still inspires today. Mariner 10 revolutionized our understanding of Mercury's geology and magnetic field in ways that continue to shape planetary science. Before its mission, Mercury was largely a blank canvas in human knowledge. Its proximity to the Sun made ground-based observation difficult, and earlier spacecraft hadn't ventured so close. Mariner 10's images revealed a planet scarred by impact craters, similar to the Moon, but with differences that hinted at a unique geological history. The vast, Smooth plains suggested episodes of volcanic activity, while cliffs known as scarps hinted at the planet shrinking as its core cooled. These discoveries painted a picture of a world shaped by both ancient and ongoing processes. The magnetic field it detected, faint but unmistakable, was a revelation, indicating that Mercury's core remained at least partially molten, defying expectations for a planet of its size. This single finding forced a reassessment of theories about planetary interiors and magnetic field generation. The mission offered valuable lessons that have rippled through decades of space exploration. Mariner 10 demonstrated the immense utility of gravity assists, a maneuver that allows spacecraft to use a planet's gravity to change speed and direction. This technique not only enabled Mariner 10's journey, but became a cornerstone of interplanetary mission design, allowing subsequent spacecraft to achieve feats once thought impossible. Another lesson lay in its use of multiple flybys to maximize data collection, a strategy adopted by missions like Galileo and New Horizons. Perhaps most importantly, Mariner 10 underscored the need for adaptability in deep space missions. Engineers and scientists had to troubleshoot navigation and instrument issues in real time, proving that flexibility and problem-solving are as critical as technical precision. The groundwork Mariner 10 laid for later missions like Messenger and Bepi-Colombo is undeniable. While it imaged only 45% of Mercury's surface, this partial coverage provided the first detailed look at the planet, sparking questions that Messenger would later aim to answer. Messenger built directly on Mariner 10's discoveries, mapping the entire surface, probing the planet's core in greater detail, and studying its mysterious exosphere. Bepi-Colombo, currently en route to Mercury, incorporates even more advanced instrumentation designed to explore the planet's magnetic interactions with the solar wind and its geological evolution. Both missions owe their trajectories, scientific focus, and technological innovations to the foundation Mariner 10 established. Today, Mariner 10 remains silent, orbiting the Sun on a trajectory that has left it a relic of its era. After its final flyby of Mercury in 1975, the spacecraft exhausted its fuel reserves, leaving it unable to adjust its course or maintain communication. It now drifts in a heliocentric orbit, a silent testament to human ingenuity. While it no longer transmits data, its journey and accomplishments endure in the annals of space exploration, a reminder of how far we've come in our quest to explore the cosmos. Mariner 10's legacy in planetary exploration is profound. It marked the first time humanity reached the innermost planet, opening a window to a realm few had dared to imagine. In the history of space exploration, it occupies a unique place as both the last of the Mariner series and a harbinger of what was to come. Its innovations in trajectory design, imaging, and scientific instrumentation set a standard that future missions continue to build upon. Remembered not just for its successes, but for the challenges it overcame, Mariner 10 stands as a symbol of exploration at its best, pushing boundaries, solving problems, and uncovering mysteries about our place in the universe. The Mariner 10 mission came with a price tag of about $98 million, a substantial sum for the 1970s, but relatively modest compared to the groundbreaking discoveries it enabled. From a scientific and technical perspective, it was considered an unqualified success. The spacecraft achieved its primary objective of exploring Mercury and exceeded expectations by capturing invaluable data about Venus during its flyby. Its pioneering use of a gravity assist maneuver and its ability to perform multiple flybys of Mercury set benchmarks for future space exploration. While some critics noted that only 45% of Mercury's surface was mapped, the overall mission was hailed as a triumph of innovation and resourcefulness, especially given the era's technological constraints. The Venus flyby, initially planned purely as a stepping stone to Mercury, yielded unexpected insights into the planet's mysterious atmosphere. Using its ultraviolet spectrometer, Mariner 10 detected complex cloud patterns and measured wind speeds in Venus's thick, carbon dioxide-rich atmosphere. These observations revealed the astonishing dynamics of Venus's atmosphere, including the discovery of superrotating winds that moved much faster than the planet itself rotated. While the dense cloud cover prevented a view of Venus's surface, the data collected hinted at the extreme and alien conditions below. This detour in the mission's path demonstrated how even secondary objectives could lead to significant scientific advancements. Mariner 10 remained operational for just over 2 years, from its launch on November 3, 1973, to March 24, 1975. The mission officially ended when the spacecraft's fuel was depleted, leaving it unable to orient its solar panels toward the Sun or its instruments toward Mercury. Without the ability to generate power or communicate with Earth, Mariner 10 became a silent traveler in the Sun's orbit. Its final months were spent executing its third and last flyby of Mercury, during which it gathered additional data and images, solidifying its contributions to planetary science. Throughout its journey, Mariner 10 faced a host of unexpected challenges that tested the ingenuity of its mission team. Early on, its star tracker, essential for navigation, encountered difficulties when it confused light from bright stars with sunlight reflecting off its own components. This required engineers to develop creative workarounds to keep the spacecraft on course. Additionally, solar radiation pressure caused unanticipated shifts in its orientation, which had to be managed with precise adjustments. Despite these obstacles, the spacecraft's systems performed admirably, showcasing the robustness of its design and the adaptability of its operators. The media coverage of Mariner 10 was a mix of fascination and measured enthusiasm. In the United States, it was portrayed as a groundbreaking achievement in planetary exploration, with major newspapers and television networks highlighting the stunning images and scientific discoveries. Mercury's cratered surface and the detection of its magnetic field made headlines, sparking curiosity about the planet's history and characteristics. Internationally, the mission was also well received, particularly in scientific circles, where it was seen as a symbol of humanity's growing ability to explore the solar system. However, public interest was somewhat muted compared to the Apollo missions, reflecting a shift in focus from human spaceflight to robotic exploration. Despite this, Mariner 10's success resonated deeply within the scientific community and inspired a generation of planetary scientists and engineers. Mariner 10 stood out among the Mariner missions for both its ambitious scope and technological innovation. Unlike its predecessors, which primarily focused on Mars and Venus, Mariner 10 ventured into uncharted territory by targeting Mercury, the least understood of the inner planets. The mission required a level of precision and adaptability beyond anything attempted in earlier Mariner missions. Its use of a gravity assist at Venus, a first in space exploration, marked a departure from the straightforward trajectories of previous spacecraft. Mariner 10's scientific payload also reflected an evolution in priorities. Its instruments were designed not only to capture images but also to analyze magnetic fields, atmospheric conditions, and surface compositions, making it one of the most sophisticated probes of its time. The differences between Mariner 10 and its successor, Messenger, highlight how far planetary science had come in the decades separating their launches. Messenger, launched in 2004, benefited from advances in propulsion, instrumentation, and data processing. While Mariner 10 imaged only 45% of Mercury's surface, Messenger mapped nearly the entire planet in high resolution, revealing a wealth of geological and compositional details. Messenger carried advanced spectrometers, magnetometers, and even a neutron detector, enabling it to investigate Mercury's composition, magnetosphere, and exosphere with unprecedented depth. Unlike Mariner 10, which only conducted flybys, Messenger entered orbit around Mercury, allowing for sustained observation over several years. This extended presence made it possible to track changes over time and explore the planet in a way that Mariner 10's fleeting visits simply couldn't. The legacy of Mariner 10 is deeply embedded in the subsequent exploration of the inner planets. By demonstrating that Mercury was not just an inert, featureless rock but a dynamic planet with a magnetic field and intriguing geology, it piqued the scientific community's interest in studying the innermost reaches of the solar system. The mission's discoveries laid the groundwork for detailed investigations of Venus and Mercury and underscored the value of exploring extreme environments close to the Sun. Its success also helped justify the development of more sophisticated spacecraft like Messenger and Bepi-Colombo, which could delve deeper into questions that Mariner 10 had only begun to address. Perhaps one of Mariner 10's most enduring contributions was its pioneering use of gravity assist techniques, a method that has since become a cornerstone of interplanetary exploration. By using Venus's gravity to alter its trajectory and gain the energy needed to reach Mercury, Mariner 10 set a precedent for efficient mission planning. This innovation was later employed in missions like Voyager, which used gravity assist to explore the outer planets, and Galileo, which leveraged similar maneuvers to reach Jupiter. The technique has enabled spacecraft to visit multiple targets within a single mission, opening up possibilities that would have been unthinkable without it. Mariner 10 proved that by carefully calculating the dynamics of celestial bodies, we could extend the reach of our probes without the need for prohibitively large amounts of fuel. The success of Mariner 10 marked a turning point in the evolution of interplanetary science. It demonstrated the feasibility of exploring challenging and hostile environments, expanding our reach beyond Mars and Venus. The mission also underscored the importance of adaptability, as the spacecraft and its operators overcame numerous technical and environmental hurdles to deliver groundbreaking results. Mariner 10 showed that interplanetary exploration was not just about reaching new destinations, but about refining techniques, answering fundamental questions, and building a foundation for the future. It was a mission that looked both forward and outward, capturing the spirit of discovery that continues to drive space exploration today. The story of Viking 1's journey to becoming the first spacecraft to land on Mars and send back data is a tale of human ingenuity and perseverance. In 1976, after years of meticulous planning, Viking 1 touched down on the rocky surface of Mars, a planet that had captivated human imagination for centuries. Engineers at NASA had spent countless sleepless nights ensuring that every calculation, every test, and every component was as precise as possible. The landing wasn't just a technical achievement. It was a moment that bridged the vast chasm between Earth and Mars. When Viking 1's instruments confirmed its safe arrival, the collective sigh of relief and celebration back on Earth was electric. This mission wasn't just about reaching another planet. It was about proving that humans could extend their reach into the cosmos and begin unraveling its mysteries. The first images sent back by Viking landers were nothing short of transformative. As the pictures slowly transmitted to Earth, pixel by pixel, they revealed a desolate but strangely familiar terrain. Mars wasn't the vibrant alien world many had imagined, but instead, it was a barren expanse of rust-colored soil and scattered rocks under a salmon-pink sky. These images were groundbreaking because they weren't just artistic impressions or interpretations. They were real. For the first time, humanity could see the surface of another planet with their own eyes, and it was both humbling and exhilarating. The images also carried profound implications for science, offering tangible clues about the planet's geology, climate, and potential for life. It was a stark reminder of how distant and yet connected we are to the universe. Viking 2 landed on Mars later that same year, complementing the achievements of its predecessor in meaningful ways. While Viking 1 focused on a flat, equatorial region, Viking 2 ventured further north to explore a colder, rockier landscape. This dual-pronged approach allowed scientists to compare findings from two distinct regions of Mars. Viking 2's discoveries expanded the narrative, showing more diverse terrain and providing a clearer picture of Mars's surface conditions. The two landers together painted a more complete image of a planet that had once been thought of as lifeless and inert, but was now proving to be far more dynamic and intriguing. Among the most surprising discoveries made by the Viking missions was the realization that Mars's surface was far more complex than anticipated. The soil contained unexpected chemical activity, including reactions that hinted at, but didn't confirm, the presence of life. This ambiguity sparked debates that have persisted for decades. The atmosphere, thinner than Earth's and composed mostly of carbon dioxide, was harsh and unwelcoming, but it hinted at a more hospitable past. Evidence of ancient riverbeds and erosion suggested that Mars might once have been warmer and wetter, a place where life could have thrived. These findings reshaped how scientists viewed the red planet, sparking new questions about its history and potential habitability. The longevity of the Viking landers was another testament to their engineering brilliance. Designed to last just 90 days, Viking 1 exceeded expectations and operated for over 6 years, while Viking 2 functioned for nearly 4 years. This endurance wasn't just a technical feat. It reflected the dedication and foresight of the teams who built and maintained the spacecraft. The landers braved freezing temperatures, dust storms, and the relentless bombardment of radiation from the sun. Their prolonged operation allowed scientists to gather an unprecedented wealth of data, extending the mission's impact far beyond its original goals. Each additional day of operation felt like a gift, a reminder of the human spirit's resilience and determination to push the boundaries of the possible. The Viking landers were equipped with a suite of instruments that reflected the bold ambitions of the mission. These tools were not just machines. They were extensions of human curiosity, designed to ask fundamental questions about Mars. The landers carried cameras to capture detailed images of the surface, spectrometers to analyze the composition of rocks and soil, and weather instruments to study the Martian atmosphere. Perhaps the most intriguing tools were the ones designed for biological experiments. These included gas chromatographs, mass spectrometers, and labeled release experiments, all meticulously crafted to detect signs of microbial life. The instruments were the culmination of years of collaboration among scientists and engineers, each piece representing countless hours of design, testing, and debate about how best to explore an alien world. Surviving on Mars required more than just ingenuity. It demanded a deep understanding of the planet's unforgiving conditions. The Viking spacecraft were designed like armored explorers, wrapped in thermal insulation to endure freezing temperatures that plummeted to -100 degrees Celsius at night. The landers were built with rugged materials that could withstand not just the cold, but also the potential hazards of Martian dust storms and ultraviolet radiation. Every part of their design, from their low-profile shape to their retractable landing legs, was engineered to cope with the unknowns of Mars. The lander's ability to endure this harsh environment was a tribute to the meticulous planning and sheer willpower of the teams who refused to leave any detail to chance. It wasn't just a technical triumph. It was a testament to the determination of humans to conquer the extremes. Communicating across millions of kilometers of space was no small feat. The Viking landers relied on a combination of high-gain and low-gain antennas to establish a link back to Earth. Data was transmitted first to orbiters circling Mars, which then relayed the information to Earth-based receivers. This system ensured that even the weakest signals could be amplified and sent across the vast gulf of space. The communication process was slow and painstaking, with images and data arriving in fragments that needed to be pieced together. Despite these challenges, every transmission was like a postcard from another world, carrying with it the hopes and dreams of those who had made the mission possible. Each beep of data felt like a whisper from Mars, a connection between two planets separated by unimaginable distances. The search for life on Mars was one of the Viking mission's boldest objectives, and it unfolded like a carefully orchestrated scientific drama. The landers conducted 3 key biological experiments, each designed to test for the presence of microbial life in the soil. In one experiment, nutrients were added to Martian soil samples to see if any metabolic processes occurred, while another tested for the release of gases that might indicate biological activity. The results were tantalizingly ambiguous, with some experiments producing reactions that could be interpreted as signs of life, while others suggested purely chemical explanations. These experiments didn't just test the soil. They tested the limits of human understanding and ignited debates that have lasted for decades. The scientists knew they were grappling with the unknown, and each result was a reminder of just how mysterious Mars truly is. The Viking landers' descent onto Mars was a ballet of precision and control, orchestrated by advanced propulsion and guidance systems. Each lander was equipped with retrorockets and a sophisticated radar system that measured altitude and speed during the descent. Parachutes deployed to slow their initial entry through Mars's thin atmosphere, but as they neared the surface, the retrorockets took over, firing in carefully timed bursts to ensure a gentle landing. The landers were designed to autonomously adjust their approach, guided by pre-programmed instructions and real-time data. It was a delicate balance between technology and trust. Trust that the systems would perform as planned, trust in the engineers who had calculated every trajectory, and trust in the courage of humanity to explore a world so far from home. The Viking missions unfolded during a time when the Cold War had driven humanity to look beyond Earth, using the stars as a stage for technological prowess and ideological competition. While the Apollo program had demonstrated American dominance in human spaceflight, the Viking missions offered a chance to extend this legacy into planetary exploration. Mars, with its tantalizing possibilities for harboring life, became the next frontier. In the context of the Cold War space race, Viking symbolized a peaceful yet competitive push for knowledge. It was not just about planting a flag, but about demonstrating that American science and engineering could answer some of humanity's most profound questions. The mission served as a quiet counterbalance to the arms race, offering a vision of what humanity could achieve when its collective efforts were aimed upward. In the 1970s, NASA was recalibrating its ambitions after the monumental success of Apollo. The Viking program perfectly aligned with the agency's goals to establish a sustained presence in planetary exploration. Mars was seen as the logical target, offering a unique opportunity to search for life and understand the evolution of planets in the solar system. Viking's objectives were ambitious but carefully defined: to study Mars's surface and atmosphere in unprecedented detail and to test for signs of life. These goals reflected a shift in NASA's strategy, moving from the immediate triumphs of human spaceflight to the longer-term pursuit of scientific discovery. Viking wasn't just a mission. It was a statement that NASA was committed to exploring the cosmos with both rigor and imagination. The Viking missions owed much to the foundation laid by earlier Mars missions, particularly Mariner 9, which in 1971 became the first spacecraft to orbit another planet. Mariner 9 had revealed a dynamic Mars with towering volcanoes, vast canyon systems, and evidence of ancient riverbeds. This groundbreaking imagery shattered previous notions of Mars as a uniformly desolate world and provided critical data for selecting Viking's landing sites. The Viking missions were, in many ways, the natural progression of what Mariner 9 had begun. While Mariner 9 had given scientists a sweeping view of the planet from above, Viking promised to bring them down to the surface, where questions about Mars's history and potential for life could be examined up close. Expectations for the Viking missions were extraordinarily high, both within the scientific community and among the general public. Scientists hoped for nothing less than transformative discoveries about Mars's geology, climate, and habitability. The possibility of finding life, even in microbial form, captured imaginations worldwide. The public, still riding the wave of excitement from the Apollo landings, looked to Viking as the next chapter in humanity's exploration of space. Yet, there was also a sense of caution. Mars was a distant and harsh world, and there was no guarantee that Viking's instruments would detect life, or even find conditions conducive to it. Still, the excitement of the unknown made Viking a mission that resonated deeply with people, blending hope with the thrill of exploration. NASA faced significant challenges in bringing the Viking program to life. Funding was a constant battle, with budget cuts threatening to derail the mission at several points. The political landscape of the 1970s, marked by economic pressures and shifting priorities, meant that every dollar spent on Viking had to be justified not just scientifically but also in terms of public and political support. Technically, the mission was an unprecedented undertaking, requiring innovations in spacecraft design, landing technology, and instrumentation. The risks were enormous. A failure would have been a devastating blow to NASA's reputation and future plans. Yet, despite these obstacles, the Viking team pressed on, driven by a shared belief in the mission's importance. The program's ultimate success was not just a triumph of technology, but a testament to the resilience and vision of the people behind it. The Viking missions began with the thunderous launch of 2 Titan II rockets, a choice driven by their proven reliability and power. These rockets were equipped with Centaur upper stages, which provided the additional thrust needed to escape Earth's gravity and set the spacecraft on a precise trajectory toward Mars. The Titan II wasn't just a tool of brute force. It was the culmination of decades of rocket engineering, a machine finely tuned to carry its precious cargo through the first leg of its interplanetary journey. Each launch was a spectacle of fire and precision, a moment when years of planning and preparation culminated in the extraordinary act of sending human-made objects to another world. The Viking orbiters and landers were designed as a symbiotic pair, each playing a critical role in the mission's success. The orbiters acted as scouts and sentinels, capturing high-resolution images of the Martian surface to identify potential landing sites and relaying data back to Earth. The landers, in turn, were the explorers, equipped to touch down and conduct detailed analyses of the surface and atmosphere. This partnership was not just a technical arrangement, but a carefully choreographed dance of engineering, where each component complemented the other. The design ensured that even in the vast emptiness of space, the Viking spacecraft operated as a cohesive whole, bridging the gap between orbit and surface. The journey of each Viking spacecraft from Earth to Mars was marked by a series of carefully planned milestones. After escaping Earth's gravity, the spacecraft entered a cruise phase, during which they fine-tuned their trajectories with mid-course corrections. These adjustments were critical, ensuring that the spacecraft would arrive at Mars on the correct path to achieve orbit and, eventually, a successful landing. As the spacecraft neared Mars, the orbiters fired their engines to slow down and enter Martian orbit, a nerve-wracking maneuver requiring perfect timing and execution. Each milestone represented a triumph of human ingenuity, a testament to the precision and adaptability required for such an audacious mission. The descent and landing phases of the Viking missions were fraught with challenges, each one a reminder of how alien and unpredictable Mars truly is. The thin Martian atmosphere offered little assistance in slowing the landers, requiring a combination of parachutes, retrorockets, and aerodynamic braking to ensure a controlled descent. Dust storms and uneven terrain added layers of uncertainty, as even the most detailed orbital images couldn't fully predict what the landers would encounter. These moments tested the resilience of the spacecraft and the foresight of the engineers who had designed them. Every second of the descent was filled with tension, a high-stakes gamble where failure was not an option. To ensure safe landings on an unknown and rocky Martian surface, the Viking landers were equipped with a suite of sophisticated systems. Radar altimeters provided real-time data on altitude and descent speed, while onboard computers made split-second decisions to adjust the retrorockets and stabilize the landing. The landers' legs were designed with shock absorbers to cushion the impact, accommodating variations in the terrain. Despite these precautions, there was no guarantee of success. Each landing was a delicate balance between trust in technology and acceptance of the inherent risks. When the landers finally touched down, they carried not just scientific instruments, but the collective hopes of everyone who had worked tirelessly to make the mission possible. When the first images and data from the Viking missions arrived on Earth, they ignited a mix of awe, curiosity, and a touch of disappointment among scientists and the public. The pictures revealed a barren, rocky surface under a dusty pink sky, a landscape strikingly alien yet hauntingly familiar. For the general public, the images were a window into another world, sparking fascination and a deeper connection to space exploration. Scientists, on the other hand, were exhilarated by the wealth of data, but tempered by the realization that Mars was harsher and less hospitable than many had hoped. The discovery of a complex but inhospitable environment stirred a profound sense of humility, as it underscored the challenges of finding life beyond Earth. Yet, it also deepened humanity's resolve to keep searching, to keep asking questions about our place in the cosmos. The scientific discoveries made by Viking 1 and Viking 2 were transformative, even if they didn't confirm the most tantalizing possibility: the existence of life. The missions revealed a world shaped by both ancient and ongoing processes. The Martian soil was found to be rich in iron, giving it the planet's signature red color, while the atmosphere was thin and composed primarily of carbon dioxide. Evidence of ancient water flows in the form of dried-up riverbeds and erosion patterns hinted at a wetter, potentially life-supporting past. The landers also recorded daily weather patterns, including temperature variations and wind activity, offering the first direct insights into Martian meteorology. Each discovery added a layer to the emerging portrait of Mars, a planet that seemed to hold echoes of a time when it might have been more Earth-like. The Viking missions profoundly influenced how Mars was perceived as a potential host for life. Before Viking, there was an undercurrent of optimism, a belief that even microbial life might exist on Mars. The results of Viking's biological experiments, however, were inconclusive. Some tests showed reactions that could hint at microbial activity, but others suggested purely chemical explanations. This ambiguity led to heated debates, with some scientists arguing that the findings could be evidence of life, while others pointed to the harsh environmental conditions as likely precluding it. The missions reshaped the narrative, emphasizing that if life had ever existed on Mars, it would likely be deep in its past or hidden away in protected niches, far from the surface. In the broader context of planetary science, the Viking missions were a watershed moment. They set new standards for robotic exploration, showcasing the feasibility of long-term missions and the value of sophisticated instrumentation. The wealth of data collected by Viking became a cornerstone for subsequent Mars missions, influencing everything from landing site selection to the design of scientific payloads. Viking's legacy also extended beyond Mars, inspiring missions to other planets and moons. It was a reminder of how exploration, even when it falls short of its most ambitious goals, can yield discoveries that redefine our understanding of the universe. The Viking missions were not without controversy. The biological experiments, in particular, sparked intense debate within the scientific community. The conflicting results, some suggestive of life, others pointing to purely chemical reactions, left no definitive answer, and this uncertainty fueled arguments for decades. Some critics questioned the design of the experiments, arguing that they might not have been sensitive enough or appropriately calibrated for Martian conditions. Others suggested that the harsh environment could have destroyed any organic materials before they could be detected. These debates underscored the complexity of searching for life on another planet and highlighted the need for even more sophisticated missions in the future. Viking's findings didn't settle the question of life on Mars. Instead, they left the door tantalizingly ajar, inviting further exploration and inquiry. The Viking missions cast a long shadow over the future of Mars exploration, serving as a template for how to approach the red planet with a combination of ambition and caution. They demonstrated that landing on Mars was not only possible but also essential for addressing the most profound scientific questions about the planet's history and potential for life. Subsequent programs like Pathfinder, Spirit, Opportunity, and Curiosity drew directly from Viking's achievements. They inherited its rigorous focus on site selection, its emphasis on collecting diverse types of data, and its reliance on sophisticated lander technology. Viking didn't just pave the way. It established Mars as a central figure in humanity's quest to understand the cosmos. The lessons from Viking were manifold and deeply influential. Pathfinder, launched more than 2 decades later, benefited from Viking's insights into Martian soil composition and landing dynamics, using an innovative airbag system that reflected evolving engineering approaches while building on the Viking legacy. Curiosity, a much more advanced mission, carried forward Viking's emphasis on comprehensive scientific payloads, where Viking scratched the surface, literally and metaphorically. Curiosity drilled into it, investigating the planet's habitability in far greater detail. Viking taught later missions how to anticipate challenges, refine biological experiments, and navigate the complexities of operating in a distant, alien environment. Viking transformed humanity's understanding of Mars's geology and atmosphere, offering the first direct measurements that revealed a planet both familiar and alien. Its findings confirmed that Mars had been shaped by volcanic activity, erosion, and ancient water flows, painting a picture of a planet with a dynamic past. The lander's weather stations tracked atmospheric patterns, showing a thin, carbon dioxide-dominated atmosphere with seasonal variations. These discoveries gave scientists a baseline for understanding the Martian environment and its evolution. Perhaps most importantly, Viking illuminated the difficulty of finding life, or even its chemical precursors, in such a harsh setting, underscoring the need for refined instruments and more focused searches in future missions. In the annals of space exploration, Viking 1 and Viking 2 stand as milestones of human achievement. They represented the most ambitious planetary science endeavor of their time, demonstrating that robotic exploration could yield groundbreaking results. Viking marked the transition from speculative science fiction to the reality of interplanetary exploration, firmly establishing NASA as a leader in space science. Its influence extended beyond Mars, inspiring missions to Venus, the outer planets, and even distant moons. Viking proved that humanity could ask big questions and pursue answers on an unprecedented scale, a legacy that continues to define space exploration today. Culturally, the Viking missions are remembered as a moment when humanity reached out to touch another world with both wonder and precision. For the public, the images of Mars's surface became iconic, symbolizing the boldness of human curiosity. Scientists and engineers who worked on the mission often reflect on it as a career-defining experience, a rare opportunity to directly contribute to expanding humanity's horizons. Today, Viking is celebrated not only for its scientific contributions, but also for its audacity and vision. It remains a touchstone for what is possible when curiosity, ingenuity, and perseverance converge in the pursuit of knowledge. The Viking program, with its dual missions, came at a hefty price tag of about $1 billion, an immense sum in the 1970s, equivalent to several billion dollars today. For a project so ambitious, its cost was frequently scrutinized, particularly during a time of economic pressures and shifting political priorities in the United States. Yet, in retrospect, the investment is often viewed as worthwhile. The missions produced a treasure trove of scientific data, established a foundation for future exploration, and captured the public's imagination. While it didn't discover life, Viking expanded the boundaries of what humanity understood about Mars, providing insights that would have been impossible otherwise. It was a reminder that exploration often demands significant resources but can yield returns that are immeasurable in terms of knowledge and inspiration. Like all pioneering endeavors, the Viking missions faced numerous challenges and unexpected anomalies. During the descent of both landers, engineers held their breath as systems had to flawlessly execute sequences to navigate the thin Martian atmosphere. Viking 1 experienced a software glitch that delayed its landing, and there were concerns about the accuracy of its radar readings due to uncertainties in terrain. The harsh Martian environment also tested the longevity of the spacecraft, with dust accumulation and temperature extremes gradually degrading components over time. Despite these hurdles, Viking exceeded expectations, with both landers operating far beyond their designed lifespans, a testament to meticulous engineering and planning. The Viking orbiters were instrumental in creating detailed maps of Mars, a contribution that extended far beyond their immediate mission objectives. They captured high-resolution images of the Martian surface, revealing features such as vast canyons, dormant volcanoes, and ancient riverbeds. These maps were not just scientific curiosities. They became essential tools for planning subsequent missions. By identifying safe landing sites and regions of scientific interest, the orbiters laid the groundwork for missions like Pathfinder, Spirit, and Curiosity. The detailed imaging also allowed scientists to hypothesize about Mars's geological history, providing a broader context for the discoveries made by the landers. One of the most unexpected aspects of the Viking missions came from the biological experiments. The results were puzzling, generating both excitement and frustration. One experiment detected chemical reactions in the Martian soil that mimicked the behavior of living organisms, sparking hope that microbial life might be present. However, follow-up experiments failed to confirm the presence of organic molecules, suggesting the reactions were likely due to the soil's highly reactive chemistry rather than biological activity. This ambiguity ignited debates that continue to this day, with some scientists arguing that the findings may have overlooked subtle signs of life, while others see them as a stark reminder of Mars's harsh, life-limiting conditions. The Viking missions were widely covered in the media, capturing headlines and imaginations both in the United States and internationally. In America, they were portrayed as a triumph of ingenuity, aligning with the broader narrative of NASA's successes in space exploration. The first images of Mars's surface were broadcast on television and printed in newspapers, becoming iconic representations of humanity's reach into the cosmos. Internationally, the missions were often celebrated as a milestone for humanity rather than just for one nation, a symbol of what was possible when science transcended borders. While some critics questioned the cost, the overwhelming public sentiment was one of fascination and pride, as Viking offered a rare glimpse into the mysteries of another world and the potential for discovery that lay beyond. The Viking missions represented a profound leap forward compared to earlier Mars missions like Mariner 9. While Mariner 9 was a groundbreaking achievement as the first spacecraft to orbit another planet, its primary contribution was in reconnaissance, capturing images of the Martian surface and identifying large-scale features such as Olympus Mons and Valles Marineris. Viking took this foundation and expanded it dramatically by actually landing on the planet. Where Mariner 9 could only observe from afar, Viking allowed for direct interaction with the Martian environment, analyzing soil, atmosphere, and weather. This progression from remote observation to hands-on science was pivotal, marking the beginning of a new era in planetary exploration. The Viking missions laid much of the groundwork for the later success of Mars rovers like Sojourner and Perseverance. Viking demonstrated how to safely land on Mars, a process fraught with challenges due to the planet's thin atmosphere and rugged terrain. It also underscored the importance of combining orbital reconnaissance with surface exploration, a model followed by every subsequent mission. The Viking landers didn't move, but their comprehensive suite of instruments and detailed analysis of a stationary site proved the value of studying Mars up close. Rovers like Sojourner, Spirit, and Perseverance built on this by adding mobility, allowing scientists to explore diverse terrains and gather data from multiple locations, a logical evolution of the groundwork Viking had laid. In comparing the Viking missions to modern Mars exploration, the differences in technology and capability are striking, yet the underlying goals remain remarkably similar. Viking's instruments were cutting-edge for the 1970s, but they were limited in sensitivity and scope compared to what missions like Curiosity and Perseverance carry today. Modern rovers benefit from decades of advancements in robotics, miniaturization, and artificial intelligence, allowing them to perform complex experiments, navigate autonomously, and operate with greater efficiency. Yet, Viking's spirit of curiosity and its ambition to answer fundamental questions about Mars's history and habitability continue to resonate in every mission that has followed. The relationship between the Viking missions and the search for extraterrestrial life is both foundational and complex. Viking was the first mission explicitly designed to search for signs of life on Mars, and its ambiguous results set the stage for decades of further investigation. By demonstrating how difficult it was to detect life, or even unambiguous signs of past life, Viking shaped the scientific strategies that guide current and future missions. It highlighted the need for more sensitive instruments, a deeper understanding of Martian chemistry, and a broader exploration of environments that might preserve evidence of ancient life. Viking didn't settle the question of life on Mars, but it made clear that answering it would require a sustained and multifaceted approach. Since the Viking missions, technological advancements have revolutionized Mars exploration, making what was once extraordinary almost routine. Improvements in material science have produced spacecraft that can survive longer in Mars's harsh environment, while advances in imaging and spectroscopy have provided unprecedented detail about the planet's surface and composition. Modern spacecraft carry instruments capable of detecting trace organic molecules, mapping subsurface ice, and even preparing for future human missions. Communication technologies now enable near real-time data transmission, and innovations like Ingenuity's helicopter flights demonstrate how far exploration capabilities have come. Yet, despite these advancements, the Viking missions remain a touchstone, a reminder of how much was achieved with the technology of their time and how they inspired the ongoing pursuit of Mars's secrets. In 1977, Voyager 1 was launched into space, embarking on a journey that would redefine humanity's understanding of the cosmos. Decades later, in 2012, it crossed a boundary no human-made object had ever reached, the heliopause. This is where the influence of the sun's solar wind ends and interstellar space begins. For scientists and engineers, this was an emotional moment. Imagine spending your entire career on a project, knowing it might outlive you. Voyager 1's entry into interstellar space confirmed that the probe was truly out there, navigating a realm beyond our solar neighborhood. The data it sent back provided direct evidence of interstellar plasma, a discovery that validated decades of work and offered a glimpse into the vast, uncharted regions between the stars. Among Voyager's many fascinating features was the Golden Record, a time capsule for anyone, or anything, that might someday encounter it. This 12-inch gold-plated copper disc carried sounds and images chosen to represent the diversity of life and culture on Earth. The record includes greetings in 55 languages, whale songs, a baby's cry, and music ranging from Beethoven to Chuck Berry. Carl Sagan, who led the team designing it, described the record as a hopeful gesture, a way of saying, "We're here. This is who we are." For those involved, the Golden Record wasn't just a scientific artifact. It was a poetic expression of humanity's desire to connect, even across unimaginable distances. Voyager 2's path through the outer solar system was a masterclass in orbital mechanics. Engineers meticulously planned its trajectory to use gravitational assists, leveraging the rare alignment of the planets to slingshot the spacecraft from one to the next. This grand tour allowed Voyager 2 to visit Jupiter, Saturn, Uranus, and Neptune, a feat no other mission has achieved. Each flyby required precise timing and careful calibration of instruments, with every success bringing exhilaration to the team on Earth. They had only one chance to get it right, and they did, capturing breathtaking images and reams of data from these distant worlds. The discoveries made by the Voyagers were as stunning as they were unexpected. At Jupiter, Voyager revealed volcanic activity on Io, the first evidence of active volcanism beyond Earth. At Saturn, it unveiled intricate structures in the rings and discovered new moons. Uranus, once a blurry in telescopes, was shown to have a tilted magnetic field and mysterious dark rings. And Neptune, with its deep blue hue, surprised scientists with its supersonic winds and a moon, Triton, spewing geysers of icy material. These findings transformed our understanding of the outer planets and their complex, dynamic systems. More than 45 years after their launch, the Voyager spacecraft are still sending data, albeit faintly, from billions of miles away. This longevity is a testament to the ingenuity of their design. Each probe relies on radioisotope thermoelectric generators, which convert the heat from decaying plutonium into electricity. Over time, the power supply has diminished, forcing NASA to turn off non-essential systems to conserve energy. The remaining instruments continue to function, gathering and transmitting data about cosmic rays, magnetic fields, and interstellar particles. For the scientists and engineers, every bit of information received feels like a gift, a whisper from the edge of the solar system, reminding us of humanity's capacity for exploration and curiosity. The Voyager spacecraft carried a suite of scientific instruments, each meticulously chosen to unravel the mysteries of the solar system and beyond. There were cameras for capturing breathtaking images, spectrometers to analyze the chemical composition of atmospheres and surfaces, and plasma detectors to measure the solar wind and its interaction with planetary environments. Each device served a purpose, piecing together a story about worlds no human would ever visit. The design team faced the immense challenge of creating instruments robust enough to survive extreme temperatures, radiation, and distance, all while ensuring they could operate with precision decades after launch. For the scientists, each instrument represented a question they had carried in their hearts for years, and every byte of data received from these tools was an answer they had long awaited. The Voyager's journeys were only possible because of an elegant trick of physics: gravity assists. Using the gravitational pull of planets like a slingshot, the spacecraft gained speed and adjusted their trajectories without using additional fuel. This maneuver wasn't just clever, it was essential. Without it, reaching multiple planets would have required a propulsion system far beyond what was feasible at the time. The engineers and navigators responsible for plotting these paths were like cosmic choreographers, carefully timing each encounter to align with the rare planetary positions of the late 1970s. Every successful flyby was a testament to their brilliance and the precision of their calculations. The propulsion and power systems of the Voyagers were feats of engineering designed to endure the unforgiving realities of space. Propulsion was managed through small thrusters fueled by hydrazine, which allowed the spacecraft to adjust their orientation for scientific observations and communication. Power came from radioisotope thermoelectric generators, RTGs, which converted heat from the decay of plutonium-238 into electricity. This system was chosen for its reliability, as solar panels would have been ineffective in the dim outer reaches of the solar system. Over time, the power output has decreased, a gradual fading of light that engineers anticipated but hoped would hold long enough for the mission to achieve its ambitious goals. Communicating across billions of kilometers posed its own set of challenges. The spacecraft were equipped with high-gain antennas that transmitted data back to Earth using a narrow beam of radio waves. To ensure the signals could be received, NASA developed the Deep Space Network, DSN, a system of massive ground-based antennas spread across the globe. Even with this infrastructure, the signals from Voyager are incredibly faint, requiring advanced processing techniques to extract valuable data. Each successful transmission feels like a conversation with an old friend who's ventured far from home. A tenuous but meaningful connection that speaks to the resilience of human ingenuity. Designing spacecraft to survive the harsh conditions of the outer planets was an exercise in foresight and innovation. The Voyagers had to withstand intense radiation around Jupiter, extreme cold in the far reaches of space, and the possibility of micrometeoroid impacts. To protect the sensitive electronics, the team encased them in a special shielded vault. Every component was tested and retested, often under conditions more extreme than those anticipated. The mission demanded perfection. There was no room for repairs once the spacecraft left Earth. For those involved, every bolt, circuit, and line of code represented a commitment to excellence and a hope that these machines would carry the best of human knowledge into the unknown. In the 1970s, the United States was grappling with an era of change, politically, culturally, and scientifically. The Apollo missions had brought humans to the moon, demonstrating unparalleled technological prowess. Yet, with the moon conquered, NASA sought its next great endeavor. The Voyager missions were born out of a desire to push further, to explore the outer planets that had always been distant enigmas in the night sky. These missions weren't just about science. They were about curiosity, ambition, and the belief that exploring the unknown was intrinsic to human nature. For the scientists and engineers, Voyager wasn't merely a project. It was a calling to chart territories humanity had never seen before. The Voyager program emerged during a time when the space race, though no longer at its peak, still influenced national priorities. The Cold War spurred both competition and collaboration in space exploration. While Apollo symbolized the race to the moon, Voyager represented a shift in focus toward deeper scientific discovery. It wasn't about beating the Soviets this time. It was about advancing human understanding of the cosmos. Voyager aligned perfectly with NASA's broader goals of demonstrating technological leadership and fostering international goodwill through scientific exploration. Its groundbreaking potential captured the imagination of a generation still dreaming of what lay beyond our planetary neighborhood. One of the most compelling reasons for Voyager's timing was the rare, grand tour alignment of the outer planets in the late 1970s. This unique arrangement, occurring roughly once every 176 years, allowed a single spacecraft to visit Jupiter, Saturn, Uranus, and Neptune by leveraging gravitational assists. It was a cosmic opportunity too good to miss. For NASA, this alignment was both a gift and a challenge. It created a strict deadline for planning, designing, and launching the missions. Missing the window would mean waiting another lifetime. The alignment gave the missions a sense of urgency and destiny, inspiring the team to work tirelessly to meet the launch dates. The Voyager missions built upon the success of earlier spacecraft like Pioneer 10 and 11, which were the first to journey through the asteroid belt and provide close-up views of Jupiter and Saturn. These missions paved the way, proving that long-distance travel through space was feasible and that spacecraft could endure the harsh environments near the gas giants. Voyager took the lessons of Pioneer and expanded on them with more sophisticated instruments, better imaging systems, and a broader scientific agenda. It was as if Pioneer had opened the door and Voyager stepped boldly through, ready to explore the wonders beyond. Funding and planning such an ambitious program were monumental challenges. The 1970s were marked by economic difficulties, including inflation and budget cuts, which placed enormous pressure on NASA to justify its expenditures. Skeptics questioned the value of sending spacecraft so far when pressing issues existed closer to home. Internally, the team had to fight for every dollar and defend the mission's scientific merit. Yet, the people behind Voyager were undeterred. They believed in the mission's importance and worked tirelessly to overcome bureaucratic hurdles, technical setbacks, and the ever-present specter of public doubt. Every problem solved, every obstacle overcome, was a testament to their resolve and their unwavering belief that reaching for the stars was worth the cost. The Voyagers were launched using Titan II rockets with Centaur upper stages, a combination chosen for its power and reliability. These rockets had already proven their capability in previous missions and were ideal for sending spacecraft on long, interplanetary trajectories. The Titan II Centaur was a workhorse, capable of delivering the Voyagers beyond Earth's gravity and onto their ambitious paths. For the engineers and mission planners, every second of the launch sequence was critical. There was no margin for error. Failure would have meant not just a loss of the spacecraft, but also the missed opportunity of a generation to explore the outer planets. Planning the Voyagers' trajectories required an extraordinary blend of precision and foresight. The rare alignment of the outer planets created a unique chance to use gravitational assists to slingshot the spacecraft from one world to the next. This technique allowed Voyager 2 to conduct flybys of Jupiter, Saturn, Uranus, and Neptune without the need for excessive onboard propulsion. Navigators calculated these paths years in advance, knowing that a single misstep could jeopardize the entire mission. Each flyby wasn't just a milestone, but also a pivot point, a chance to fine-tune the spacecraft's path for the next encounter. The science teams ensured that every maneuver maximized opportunities for data collection, squeezing as much knowledge as possible from each planetary visit. The journey of the Voyagers through the solar system was punctuated by incredible milestones that pushed the boundaries of human knowledge. Voyager 1 provided the first detailed images of Jupiter's Great Red Spot and the volcanic activity on its moon Io, revealing a dynamic system that defied previous assumptions. At Saturn, it captured the ethereal beauty of the planet's rings and discovered moons like Titan, with its thick atmosphere of nitrogen and methane. Voyager 2's encounters with Uranus and Neptune were particularly groundbreaking. It showed Uranus as a pale blue-green orb with dark rings and a magnetic field unlike any other, and Neptune revealed its intense storms and Triton's icy geysers. Each of these moments was a triumph, a realization of years of careful planning and tireless dedication. Voyager 2's ability to visit Uranus and Neptune after its Saturn flyby was a triumph of engineering and navigation. By carefully timing its approach to Saturn, the spacecraft used the planet's gravity to redirect its trajectory toward Uranus. The process repeated at Uranus to set a course for Neptune. These maneuvers required pinpoint accuracy and coordination, as even minor deviations could have thrown the spacecraft off course. For the mission team, every successful maneuver was a relief and a victory, the culmination of countless calculations and simulations. To keep the Voyager's instruments functional during their long journey, engineers employed several ingenious techniques. Power conservation was critical, as the radioisotope thermoelectric generators, RTGs, gradually produced less electricity over time. Non-essential systems were shut down when not in use, and the instruments were periodically tested to ensure they remained operational. Thermal control was another challenge, as the spacecraft had to endure the frigid cold of deep space. Engineers designed systems to redistribute heat generated by the RTGs, ensuring critical components stayed within operational temperatures. For the team, every transmission from the spacecraft, no matter how faint, was a reminder that their careful planning and resilience had paid off, keeping these emissaries of Earth alive and working far longer than anyone had dared to hope. When the Voyager spacecraft sent back their first close-up images of Jupiter, the reaction was electric. Scientists marveled at the intricate details of the planet's swirling storms and the surprising volcanic activity on its moon Io, the first evidence of active volcanism beyond Earth. For the public, the images were awe-inspiring, a reminder of the vastness and beauty of the universe. News broadcasts and magazines featured the photographs prominently, sparking wonder in people who had never imagined such dynamic and alien worlds. At a time when space exploration was competing with other societal concerns, Voyager's images reignited a collective sense of curiosity and pride. The discoveries at each planet were groundbreaking. At Jupiter, the Voyagers revealed a world of immense storms and discovered that Io's surface was alive with eruptions of sulfur and other materials. Saturn's rings turned out to be far more complex than previously imagined, with intricate structures shaped by the gravitational influences of its moons. Uranus, once thought to be a bland and featureless planet, surprised scientists with its tilted magnetic field and faint, dark rings. At Neptune, the spacecraft found the fastest winds in the solar system and observed Triton, a moon with active geysers spouting icy material into space. These findings were not just incremental. They fundamentally altered our understanding of the outer planets and their moons, showing them to be dynamic and varied worlds rather than static, cold objects. The Voyager missions transformed planetary science, offering new insights into the behavior of planetary atmospheres, magnetic fields, and ring systems. Before Voyager, much of what we knew about the outer planets was based on distant telescope observations. The missions turned blurry dots of light into vivid landscapes with unique geologies and atmospheres. The discovery of active processes on moons like Io and Triton expanded the search for potential habitable environments beyond Earth, reshaping our approach to exploring the solar system. Voyager showed that even the farthest reaches of our planetary neighborhood were full of surprises, encouraging scientists to ask new questions and propose new missions to build on its legacy. For many, the Voyager missions were a source of inspiration. They demonstrated what was possible when humanity united in the pursuit of knowledge. Young scientists and engineers who saw the images from Voyager were often inspired to pursue careers in space exploration, astronomy, and engineering. The missions became a symbol of perseverance, creativity, and the power of human curiosity. Decades later, their influence could still be felt in missions like Cassini, New Horizons, and the upcoming Europa Clipper, all of which owe a debt to the trailblazed by Voyager. The golden record, carried aboard both spacecraft, was as much a philosophical statement as it was a scientific artifact. Its messages and music, intended for any extraterrestrial life that might encounter the spacecraft, have sparked countless discussions about humanity's place in the universe. What should we say to the cosmos, and how should we represent ourselves? The record is a time capsule of life on Earth in the late 20th century, a hopeful gesture that transcends borders and conflicts. For many, it symbolizes our desire to be remembered and to connect, even across the vast emptiness of space. It continues to inspire debates about humanity's legacy and what it means to reach outward into the unknown, knowing that someone, or something, might one day listen. The Voyager mission set the stage for a new era of exploration, directly influencing the design and objectives of later missions like Galileo, Cassini, and New Horizons. By showing the complexity and dynamism of the outer planets, Voyager underscored the need for dedicated, long-term studies of these worlds. Galileo followed by studying Jupiter and its moons in unprecedented detail, building on Voyager's discoveries, such as Io's volcanism and Europa's icy surface. Cassini took this further at Saturn, spending over a decade uncovering the intricate interactions of its rings, moons, and magnetic field, all guided by Voyager's pioneering insights. New Horizons, which flew by Pluto in 2015, was another spiritual successor, proving that even the most distant objects in our solar system could be revealed as rich, dynamic environments. Without Voyager, these missions might not have been conceived, or at least not with the same depth of understanding or ambition. When Voyager 1 crossed the heliopause in 2012, entering interstellar space, it was more than a scientific milestone. It was a deeply human moment. For the first time, an object built by human hands had left the bubble of our sun's influence, venturing into the vast, uncharted void between the stars. The data Voyager sent back from this transition, including measurements of interstellar plasma, gave scientists their first direct insights into the conditions outside our solar system. But beyond the science, Voyager 1's crossing was a poignant reminder of humanity's reach. A tiny spacecraft, launched decades earlier with finite technology, had become our ambassador to the stars, carrying with it the story of Earth and its inhabitants. The Voyagers also revolutionized our understanding of the heliosphere, the protective magnetic bubble created by the sun's solar wind. By studying the boundary regions where the solar wind interacts with interstellar space, the missions provided crucial information about how our solar system is shielded from cosmic radiation. These findings have implications not just for understanding the sun's influence, but also for the conditions that might affect life on Earth in future interstellar missions. For the scientists analyzing this data, it was like peeling back a layer of cosmic mystery, revealing the dynamic nature of a region that had previously been theoretical. The lessons learned from Voyager have shaped modern space exploration in countless ways. The use of gravitational assists, the long-term reliability of radioisotope thermoelectric generators, and the ability to operate spacecraft remotely over decades have all become standard practices. Voyager also taught engineers the value of building for longevity and adaptability. The spacecraft systems have been reprogrammed and reconfigured many times since launch, extending their lifespans well beyond initial expectations. These lessons are reflected in missions like the Mars rovers and the James Webb Space Telescope, where long-term planning and robustness are critical. In the history of space exploration, the Voyagers hold a special place as symbols of human ingenuity and curiosity. They represent a time when ambition and imagination drove us to look beyond our immediate horizons, seeking to understand not just our neighboring planets, but also our place in the cosmos. Their golden records remain a testament to our desire to connect, even across the unimaginable distances of space. Today, the Voyagers continue their silent journey, carrying with them the dreams of those who built them and the legacy of a generation that dared to reach for the stars. They are remembered not just as scientific triumphs, but as enduring emblems of what humanity can achieve when we dare to explore the unknown. Keeping in touch with the Voyager spacecraft across the vastness of space has been a monumental challenge, requiring constant innovation and ingenuity. As the spacecraft moved farther from Earth, their signals weakened to a whisper, trillions of times fainter than the power of a standard radio broadcast. Engineers at NASA's Deep Space Network, DSN, had to develop new techniques to detect and decode these faint signals, including upgrading ground-based antennas and using advanced signal processing methods. Over the decades, the spacecraft's aging hardware posed additional challenges as components wore out or degraded in the harsh conditions of space. The mission team adapted by reprogramming the spacecraft from billions of kilometers away, a feat of remote engineering that has kept them operational far beyond their original design life. Each day of continued communication feels like a small miracle, a testament to the persistence and creativity of the engineers who refuse to let these interstellar explorers fall silent. The Voyager program, with its decades of scientific achievements, came at a surprisingly modest price by modern standards. The total cost of the program, including development, launches, and operations over 45 years, is approximately $1 billion. While this might seem like a significant sum, it amounts to just a few cents per year for each American taxpayer. Considering the breadth of knowledge gained and the inspiration sparked by the missions, most scientists, policymakers, and the public view it as one of the most worthwhile investments in the history of space exploration. The data collected have shaped our understanding of the solar system, and the mission's enduring legacy has demonstrated that the pursuit of knowledge is a priceless endeavor. While the Voyagers are celebrated for their iconic discoveries, such as Io's volcanism, Titan's thick atmosphere, and Neptune's supersonic winds, they also made less publicized findings that expanded our understanding of the solar system. For instance, Voyager 2 discovered that Uranus has an unexpectedly tilted magnetic field, likely due to an off-center internal dynamo, and that Neptune radiates more heat than it receives from the Sun, suggesting active internal processes. The spacecraft also revealed the existence of faint planetary rings around Uranus and Neptune, subtle structures that had been invisible from Earth. These smaller discoveries were no less significant to the scientific community, as they challenged existing theories and opened new avenues of inquiry into the nature of planetary systems. The cultural impact of the Voyager missions and the Golden Record has been profound, inspiring countless works of art, music, and literature. The record itself, a time capsule of human culture, has captured the imagination of artists and thinkers, symbolizing humanity's hope to connect with other intelligent beings. Musicians have composed symphonies and albums inspired by the concept of sending a message to the stars, while filmmakers and authors have used the missions as a backdrop to explore themes of exploration, loneliness, and the search for meaning. Carl Sagan's involvement with the Golden Record Project and his poetic reflections on Voyager have particularly resonated, cementing the spacecraft's place as an emblem of human curiosity and unity. Voyager's journey, both scientific and symbolic, continues to remind us of our shared desire to understand and to be understood, whether by distant civilizations or by ourselves. The Voyager missions built upon the success of Pioneer 10 and 11, but went far beyond what those earlier trailblazers achieved. Pioneer 10, launched in 1972, was the first spacecraft to pass through the asteroid belt and reach Jupiter, while Pioneer 11 followed with a close encounter of Jupiter and the first ever visit to Saturn. These missions demonstrated that spacecraft could survive the rigors of the outer solar system, laying the groundwork for the far more ambitious Voyager program. While Pioneer missions provided the first glimpses of these distant worlds, Voyager carried a more sophisticated suite of instruments and was designed to not only take better images, but also to analyze planetary atmospheres, magnetic fields, and moons in unprecedented detail. The Pioneers were like scouts clearing the way, while the Voyagers became explorers, revealing the richness and complexity of the outer planets and their environments. The success of the Voyager missions was a pivotal moment in the evolution of interplanetary exploration, shaping the way modern missions are conceived and executed. They proved the value of gravitational assists, a technique that has since become a cornerstone of interplanetary travel, allowing spacecraft to reach distant destinations with minimal fuel. Voyager also showcased the importance of long-term mission planning and adaptable spacecraft design. Missions like Galileo, Cassini, and New Horizons borrowed heavily from Voyager's approach, using similar methodologies to maximize scientific return and longevity. The lessons learned from Voyager's operations, including the challenges of deep space communication and power management, continue to influence every mission venturing beyond Earth's orbit. The Golden Record stands apart from other human-made artifacts sent into space, not only because of its ambition but also because of the philosophical questions it raises. Earlier artifacts, like the Pioneer plaques, were simpler, etched metal plates with basic information about humanity and Earth. The Golden Record, however, was a far richer and more complex endeavor, including music, images, and sounds meant to convey the diversity of life and culture on Earth. It's a statement of humanity's desire to connect and be remembered, regardless of whether it is ever found by extraterrestrial beings. Unlike scientific instruments or mission hardware, the Golden Record carries no practical purpose. Its presence aboard Voyager is purely symbolic, a testament to our curiosity and our need to leave a mark on the cosmos. Since Voyager 1 crossed the heliopause in 2012, our understanding of interstellar space has expanded significantly. The spacecraft revealed that this boundary, where the sun's influence ends and the interstellar medium begins, is far more complex and dynamic than expected. Instead of a clean transition, Voyager detected fluctuations in plasma density and waves caused by interactions between solar wind particles and the interstellar medium. This data has given scientists their first direct glimpse into the environment beyond the heliosphere, helping to refine models of how the sun interacts with the galaxy. These findings are more than just scientific. They represent the first time humanity has reached into the space between stars, a profound milestone in our exploration of the universe. Voyager's data has also influenced theories about the solar system's formation and evolution. The detailed observations of planetary atmospheres, magnetic fields, and moons have provided critical clues about how the outer planets formed and how they shaped the solar system. For instance, the discovery of active geology on moons like Io and Triton suggests that tidal heating, caused by gravitational interactions with larger bodies, plays a significant role in shaping planetary systems. Similarly, Voyager's studies of Saturn's rings and Neptune's dynamic atmosphere have helped scientists understand the processes that govern planetary weather and ring system formation. These insights continue to inform current research, showing how our solar system fits into the broader context of planetary systems across the galaxy. Voyager's legacy is not just what it discovered, but also the questions it inspired, questions that drive the next generation of exploration. As we close the book on the daring missions of the 1970s, it's hard not to marvel at just how much we accomplished in such a short span of time. From robotic pioneers scooping lunar soil to spacecraft braving asteroid belts and interstellar space, the decade was nothing short of extraordinary. These missions weren't just about exploring planets. They were about exploring our potential, pushing the limits of what humanity could dream, build, and achieve. Thank you for joining me on this journey through time and space here on Quiet Universe. If you enjoyed this trip through the cosmos, don't forget to leave a like. It's like your little gravity assist, helping this channel go farther. And if you haven't already, hit that subscribe button and become part of this ever-expanding galaxy of curiosity and wonder. Until next time, may your nights be calm, your thoughts be vast, and your dreams take you to the stars. See you soon.